Okay. So, first of all, I would like to introduce Professor Maiorana, which is the president of the Academy of Science and Letters. And I think that we are just in the building of this academy. So, please.
Thanks, Gianpaolo. Good morning, everyone. I'm very glad to host this meeting, and on behalf of our academy, I welcome all who are with us today attending this very interesting meeting, whose title is, in my opinion, really appealing: Passion for Earth. As you know, this in words is everyone's passion. Unfortunately, the reality is different. So I think that this meeting is very welcome to remind us the complexity of problem that the science has to face today. Also, appealing are the panel of speakers and the title of their communication. So I'm sure that the meeting will be successful, even if I won't be able, I apologize for that, to attend it for all the day. I don't want to take away much time from scientific work, so I'm ready to give the word to Professor Angela Bracco, President of the Italian Society of Physics and corresponding member of the Istituto Lombardo. She's also going to chair the first session of the meeting.
Okay, thank you very much. Professor Maiorana, is this open?
Yes.
See? No.
Okay, no, okay. To Professor Maiorana, and also, of course, to Gianpaolo Bellini, that has the idea to organize this particular event, Passion for. So Passion for, in this case, is for Earth, are some events that we, as Italian Physical Society, we started a few years ago when the president was Professor Cifarelli. And in this year, that is the year in which we celebrate 125 years of the existence of our society, we had three special Passion for. We had one in the summer in Varenna that was dedicated to the International Year of Basic Science for Sustainable Development. We have this one, and the next one will be Passion for Glass in Bologna at the Academy of Science there. So we are very grateful to the academies to help to organize this, in particular to the Istituto Lombardo that has given the possibility to use this very nice room, very fascinating, full of history. And I think also this is font of a source of inspiration for us and create a good atmosphere also in connection to what we are discussing today. So as it was pointed out, the program is very appealing. We thank the speaker, and I think we will enjoy very much these days all together. And thank you very much for again to Gianpaolo for putting together such an exciting, interesting program. Okay, so I don't have much to say.
Okay,
that we are proud, and thank you very much.
Yes, I think that a few words only that we have 2 coffee break, and the catering is organized in the room adjacent to this. And there is also a change in the program, because Fabio Mantovani is unable to come because he has important family problems. Then we have that Nanami Kawada, we start at 14:10 replacing Livia Ludhova. Livia Ludhova will start at 2:45, and she absorbs also the talk of Fabio Mantovani. I think those other ones, there is no other changes. I think that we left 10 minutes after eagerly talk for the discussion, including the discussion by the people connected in streaming. So, okay, we can start.
Okay, we can start and then I will go down. Yes, I have the program also here. Thank you very much. Okay, so now I think we can start the first section. And it's a pleasure for me, I introduce this from here now, Professor Cinzia Farnetani from the University of the Paris Cité. And she will talk about composition and geodynamics of she's a geophysicist. And so we are really glad now to listen to your presentation. Okay, I go down. Is that okay?
Well, if you use a microphone or not, I have to. Okay, if I have to. Hello, well, thanks for organizing this and for inviting me. And I would like to start, well, the first slides, maybe back here. I will talk about composition and geodynamics of the Earth. And I would like to start my presentation with this conceptual view of Earth evolution. And it was proposed by Dave Stevenson. And please note that on the axis, you have this and that. So it could be anything. It could be temperature, composition, put what you want. And this tells us that we will start with an initial condition, and this is our cosmic heritage. This depends on the nature and on the origin of a material that constitute the Earth, and of course, the physics of the formation processes. Then you have an evolutionary path that brings us to present state. And in this evolutionary path, we have physical and chemical processes that can act on different timescales. For example, processes that happen very early after the formation of the Earth. For example, the differentiation between a silicate mantle and a metallic core, loss of volatiles, and other processes. Then we have very slow processes that happen on very long timescales. And this, for example, is solid state mantle convection and plate tectonics. And so we arrive to the present state. And as you see, Dave Stevenson is a geophysicist. So he claims that only geophysics can elucidate present states. Of course, this is not that true or not enough, even if, what if I say, no, back. What if I say next and you change the slide? Present state, that's a cut of Earth. And I would say that there is a good agreement upon the fact that the Earth is a differentiated planet with a metallic core and a silicate mantle. And we also agree on the fact that there are 8 big elements, or the big 8, that basically represent 99% of the mass and the atomic proportion of Earth. And these are the elements, okay? But besides that, many things are still a matter of debate. And certainly, the Earth mantle is likely to be heterogeneous, okay? And once again, these are seismologists that tell us that there are seismic velocities anomalies at the bottom of the mantle. And over the years, many authors pointed out that there are 2 particular zones, particularly interesting. And these are what is called the ultra low velocity zones. And these are patches at the bottom of a mantle. So again, this is the mantle, this is the core. If we are looking, thanks to seismologists, at the bottom of the mantle, we see these patches. Here the velocity, the seismic velocity is incredibly low, up to 30% reduction in Vs and 10% in Vp. I hope we sort of understand this basic about seismologists. And in order to obtain this, you basically need a 10% density increase, which is a lot, and which can be made through iron. Then there are also other zones that are heterogeneous, and these are called large low shear velocity provinces. They cover up to 25%, 50% of a core mantle boundary. And here the velocity reduction is of the order of 2%. And there is still debate on the nature of these things. Now, this is just to show what seismologists can tell us, which is really beautiful. If we look at the cut at 2,800 kilometers depth, so this is really the base of a mantle, and the colors tells you about velocity reduction of the order 2%. We see beneath the Pacific and beneath Africa, these large low shear velocity provinces. And if we do cross-cut, for example, across the Pacific, and now this is a cross-cut, that's a surface, that's a core mantle boundary, what do we see? We see the seismic velocity anomalies rising up through the whole lower mantle and probably affecting surface volcanism like hotspot volcanism. Something similar we see also beneath the French Polynesia. Here at depth you have large zones of low velocity anomalies. Next. Just to finish up with what the main message from seismologists. Now, if we look, this is a cross-cut at 1,000 kilometers depth, and I underlined 3 zones here, A, B, C, A, B, T, and here you see that the colors are blue, so the seismic velocities are faster than what expected. What's there? Well, we know that the oceanic lithosphere is cold and subducts. And in some subduction zone, the lithosphere dips down in the lower mantle without, say, any problems. But in other cases, in other subduction zone, it seems that the cold plate subducts and then somewhat stagnates at a depth of 660 kilometers. Now, we know what happens at 660 kilometers is a phase transition of olivine to perovskite and magnesiowoostite, so other minerals. What happens instead at 1,000 kilometers depth? That is still a matter of debate. But sure it is that seismologists tell us that some slabs seems to pond or stagnate also at these depths. So that's part of a message from seismology. And now we look at the message that what petrologists can tell us. Now we know that at the Earth's surface we have 60,000 kilometers of spreading ridges, and here the plates diverge, you have partial melting, and you create new oceanic crust. These are basalts and are called MORB, mid-ocean ridge basalts, and the general view was to consider that basalts are depleted because they represent a sort of residual after crustal extraction. So when geochemists go and look and sample all these basalts, they found that some basalts are indeed depleted. When you say depleted, is depleted in incompatible elements. And some other MORBs instead are enriched in incompatible elements. And the classical view was to say, well, these MORBs are enriched because they are close to hotspot. That's a traditional view. So you see hotspot in red and enriched MORB in green. But ever since Gale came up with a new view and said, we find enriched basalts also far from hotspot. So they should not be excluded when we try to understand the composition of MORBs. So this is really a new view, and it is important. Why it is important for you guys or for us? It is important. I won't enter in the details of this kind of diagram, but these are trace element patterns. Here are the trace elements, and I underlined the thorium and uranium. They are there. Now, all these dashed lines are the values that you find generally in the literature. Instead, with solid lines are the values that have been proposed by Gale if you don't exclude in your composition of MORB the enriched MORB. Okay. So what matters for you is concentrations, new concentrations in uranium and thorium, and also estimates for the potassium-uranium ratio, which comes from MORB. Their value is actually similar to what's found in the literature, but is actually lower than what's suggested by Arevalo. And we will see in a second that all this goes into models. Now, why should we care about MORBs? Well, we care about MORBs because in order to understand the composition of the Earth, we cannot work only with compositions of chondrites. We need to work at a certain time with composite samples from meteorites, but also from today upper mantle. Why did I talk about chondrites? Because the meteorites, they are classified, I won't enter in the details, don't worry, but the meteorites are classified into undifferentiated meteorites and differentiated meteorites. What does this undifferentiated means? It means that what we see today on Earth are fragments of small bodies that didn't differentiate into a core and into a mantle. So this could be the ideal samples to understand the composition of Earth. And I will talk only about chondrites, and among chondrites, we have different types of chondrites. I will talk about carbonaceous chondrites, which represent a small fraction of all the meteorites that fall on Earth, enstatite chondrites, another small fraction, and a bigger fraction is ordinary chondrites. Okay, so let's start to see the differences between two main types of chondrites. First of all, let's be clear, there is no single chondrite that has a composition of Earth. So we cannot just look at chondrites. The main two best candidates would be enstatite chondrites and carbonaceous chondrites. Now the enstatite chondrites, to put it simply, they are full of silica. There is a lot of silica. So since there is lots of silica, of course, when you look at the ratio aluminum silica or magnesium silica, the enstatite chondrites have very low ratios because they have lots of silica compared to carbonaceous chondrites, which will be up here, and the Earth, which is up here. If we go back to enstatite chondrites, they also have low oxygen. And this has profound implications because when you look at oxygen, you look at iron, which is if it is oxidized or not. And then obviously, enstatite chondrites have very low oxidized iron because they don't have oxygen and very high ratio of iron over silica with respect to carbonaceous chondrites, which are instead down here. So these are two main differences. There are also other differences. Enstatite chondrites have very low volatile abundances. Carbonaceous chondrites have high. And then there are differences in the isotopic compositions, etc. So the point here is that no single chondrites defines the composition of the Earth. Now, let's start looking at behavior of elements. Now I will focus on uranium and thorium, and these two elements in all chondrites. It's amazing. In all chondrites, they can have different concentrations, but their ratio is all identical. You see, carbonaceous chondrites, enstatite chondrites, they all fall on this line where thorium is equal 3.5 times uranium. Okay? How comes that these elements have this behavior? Well, we know that uranium and thorium are what is called refractory elements. And these refractory elements are defined by very high condensation temperatures. Okay, this is a temperature where 50% of the element is condensed for forming minerals. If we are looking instead at potassium, the other heat-producing element, potassium is down here. It has a low condensation temperatures, and indeed potassium is a volatile element. So on this diagram, we see the concentration of Earth normalized over concentrations of chondrites. So since potassium is volatile, we need to work out some ratios like potassium uranium in chondrites is very high, in the Earth is low, and this tells us that the Earth's lack probably 85% of its volatile. Now, this is a busy diagram, but stay with me for a second. Again, on this axis, we have a condensation temperatures, and these are abundances normalized by CI chondrites, similar to what we saw before. What we saw before was only the bulk Earth, okay? So these are these gray dots, refractory elements, volatile elements. The information that is added in this figure concerns the mantle. And so the squares give the mantle composition. With green squares, you see the concentrations of lithophile elements. These are elements that like to stay in the mantle, in the silicate part. Therefore, if we form the core, the mantle will be enriched in these elements with respect to the bulk curve. We all agree on this, and this enrichment factor is on the order of 1.5. Then we have the elements that so the refractory elements, they always gain, okay? Whereas in the mantle, we also see siderophile elements. So these are elements that like to go in the core, and therefore in the mantle, they have relatively low concentrations. Now the other issues, if we all agree of what happens to all these elements once we fractionate, we form the core, the other big problem is to understand what happens when we lose volatiles. And so these enrichment factors that we have to consider when we lose volatiles depends on the type of chondrite we started with. If we started with an enstatite, there is not much volatile, so the enrichment factor is basically 0. If we start with carbonaceous chondrites instead, since they have lots of fluids, this enrichment factor has to be pretty high. And that's a matter of debate, okay? Now, I will show only one table. I know you don't have to show tables, it's a rule, but I will show only one table. And in this table, I would plot the compositions for the bulk silicate earth, which means the silicate part once we subtracted the core, so it's mantle and crust all together with different oxides and heat-producing elements that are of interest here. If you start with the chondritic enstatites, it was a model by Marc Javois. The problem with this model is that you have so much silica that in order to fit the upper mantle compositions known from orbs, you need to put lots of silica in the lower mantle. So this model suggests a different compositions between upper and lower mantle. The other sort of problem is that in this, if you start with chondritic enstatite, you have relatively low concentrations of heat-producing elements with respect to other models that we will talk about in a second, derived, for example, McDonald and Son, derived from chondrites and from constraints from the upper mantle. Now, that's not the whole story, because we also need to form the crust. So chemical differentiation and extraction of a crust comprises, of course, trying to understand the composition of a crust and use seismic measurements like the thickness, the density of a crust. And once we do, imagine we do all this, we find that the concentrations of heat-producing elements in the continental crust is incredibly high. You see, I put everything in ppb, part per billion. This is uranium in the crust, this is uranium in the depleted mantle. So the crust is a huge reservoir of heat-producing elements. And here I also introduced the amount of heat, terawatts, that is produced by these heat-producing elements. And I will know how to know the heat flow out of the Earth. Well, the heat flow, this is a global map of heat flow out of the Earth. And we see, so red colors is high heat flow, basically along spreading ridges, blue, low heat flow, basically on continents. How do we know all this? Well, these are field measurements. And when we go and you measure, you send a cable in a borehole and you measure temperatures at different depths so that you can calculate temperature gradients. And then you take rock samples, you go in the lab and you measure thermal conductivity. So that's a lot of work. And they end up with a continental heat flow of order 14 terawatt. Considering the oceanic flow, this relies on direct measurements and also on models, theoretical models of how the lithosphere cools. And then you have to add a small contribution from hotspot. So all in all, the oceanic heat flow amounts to 32 terawatt. And when you sum the two, you have how much heat flow the Earth is losing. Okay, terawatts, so this is joule per second. Okay. Yes? No, that's a bulk, that's a hole. When you go at the surface, you don't know what comes up. Oh, the maximum, they go deep 2 kilometers. That's, yes, yes, but in some way, the heat flow that you, at 2 kilometers, you measure temperature at different depths, so you have a temperature gradient. And this somewhat integrates all the heat that is produced in the crust and comes up. So the value of a crustal heat flow is not restricted to the first 2 kilometers that you measure, but integrates all the heat that is produced in the crust.
In that case, we had to assume that the distribution is adiabatic, is not okay.
Well, in the crust, wait a second. In the crust, you don't have adiabatic. The temperature gradient that you have in the crust is dictated by thermal diffusion. Okay, and you have a certain gradient. We rather talk about adiabatic temperature gradient when we are in the mantle, and it is advection that dictates how temperatures varies with depth.
Just let me finish my
yes, sorry.
But this means that you assume that in the mantle, the distribution of the nuclei producing heat is homogeneous.
Yes, that's true.
But this is not.
This is not true.
Is
okay.
Not, no, it's not. We don't know.
Yeah,
okay.
we don't know. So indeed, the next step, the first step is to say, let's try to constrain through surface measurements, because this is what we can do, the heat flow that is coming out from the Earth. And then the next step is to say, where does this heat come from? That's another question, and maybe that's a question you want to address. And I know that Davis will give a talk on heat flow and so on. So I will touch very, very briefly, don't worry, on these main ingredients, because I think you will do it. But I felt that I couldn't prepare a talk without saying anything about it. Okay, so let's take the surface heat flow 36 by Claude Jopard. The question is, where does this stuff come from? Okay, now. We already mentioned radiogenic heat production in the crust. Then these are the mantle contribution. I will talk about it in a second. And there is a contribution from the core, because the metallic core is cooling. Okay, so this core cooling is actually calculated by considering thermal cooling, because of thermal cooling of latent heat from inner core crystallization, and also a thermal part that is related to compositional energy, because inner core is actually crystallizing. The question for you could be, could we put some heat-producing elements in the core? It's a big question. And here I only touch upon these high pressure and temperature experiments done by the keep in Paris by James Badrow. Basically, they have liquid iron, liquid silicate, and they calculate the partition coefficients. And they come up with the idea that 4.5 billion years ago, you could put in at the maximum 3.5 ppb uranium, 26 ppm potassium, that would produce 7.5 terawatt back then, so that today, basically, you couldn't produce more than 1 terawatt of radiogenic heat in the core. So this is the heat flow from the core. And this is a mental secular cooling. I won't go too much in detail, but it's obvious that if you take what is coming out from the Earth minus what is produced in the crust, you have what the Earth is losing, and this is more than the input, which is radiogenic mantle and the core. So the difference is around 18 terawatt, and this is what we call the secular cooling. The Earth is cooling down, and there are I will cite only two implications of this. The rate of mantle cooling, which is estimated around 100 degrees per billion years, and the convective Urey ratio, and I think that Davis will talk about it, so no, I say no, okay. So it's a ratio of internal heat generation in the mantle over the heat loss where we subtracted the contribution to the crust. Now this convective Urey ratio is used in parameterized models in order to understand the thermal evolution of the Earth. So it's quite important. Now that we know all this, let's go back to our table. And without going in the details again of what we mentioned, this is a continental crust, the depleted mantle, the bulk silicate Earth, and this is the heat production of each term. The question here is, do we need a hidden reservoir? This idea of a hidden reservoir has been around for years. And if you ask to some researchers, they would say, yes, of course. Since if you add up the heat produced by the depleted mantle plus the heat produced by the crust, you find a value which is much lower than the bulk silicate Earth. So you need to have part of a lower mantle that is enriched in heat-producing elements. Other researchers would tell you no. For example, if you ask Korenaga, he would tell you no, because we don't know well enough the heat that is produced inside the crust, because the lower continental crust is a bit mystery. The production of a depleted mantle could be higher, and this would go in the direction that we just saw the values suggested by Gale and co-authors, or the bulk silicate Earth value could be lower. So this is still actually a big matter of debate, and if you as a community could help us understand where to put, if we need an enriched reservoir or not, would be very, very helpful. And this, of course, goes through better understanding of a crust. Now, just to finish up, I would like to say that during the last years, geochemists tended to propose models where you form an early enriched reservoir. What does this mean? It means that very, very early, say at 4 billion years ago, you form an enriched reservoir. In this model suggested by Hoffman and co-authors this year, they are in favor of producing an early crust. And then this early crust is subducted, and part of it stays hidden forever and would form a hidden reservoir down here. If you don't like the idea that something is hidden, then you can send it to space, and these are the model of collisional erosion. Just saying, there is a collision, the crust goes and is gone forever. So what we are left with is with a global mantle that is an early depleted reservoir. It has been depleted by the formation of its early crust. And I won't enter in the details, but now that we have short-lived isotopes like the system hafnium tungsten or some isotopes of samarium neodymium, more and more geochemists are in favor of this kind of model. And in order to stabilize a primitive reservoir, these are numerical simulations by Nakagawa and Takli. Here we see with the color scale a primitive reservoir, so lots of primitive reservoir is saved, and these three different models correspond to three different excess density of this primitive material. The idea is that if you want to hide something and keep it down there forever, it needs to be compositionally denser or more viscous. If it has the same composition of a mantle, then mantle convection will stir it up, and there is no way you can hide something. Okay? And these are my lights. How do I go with time? Okay, I go on. Few minutes? Okay, fine. So these are my last slides. These are my last slides. And I would like to talk about some laboratory experiments that we conducted in our lab. We started a few years ago, and the idea was to be able, for the first time, to reproduce mantle convection with internally heated. And this had never been done before, so we are the only team in the world able to do so. And in order to do so, we started with a microwave oven, and for basically 1 year, we modified this oven in order to be certain that inside the microwave oven, you would heat absolutely uniformly up to 4.5 liters of fluids for several hours. So this is a tank that we use, is filled with fluid, is water, nitroso, and we can reach high Rayleigh numbers of 10 to the 4, 10 to the 7. I guess you know what a Rayleigh number is, but basically it's non-dimensional numbers that gives the vigor of convection. And we think that the Earth has a very high Rayleigh numbers. And inside this convecting fluid, then we had to measure temperature and velocities. So we applied lots of holes and things like that in order to see inside our tank. Okay. Now, when we started, we used a uniform fluid. Now, if you have a uniform fluid that is heated only from within, what you expect to see is cold subducting material or cold stuff that sinks down. And you actually see here somewhat cold currents. You can visualize the errors. There is downgoing flow here and here. And if you when you calculate the non-dimensional temperature across the tank, you obtain this profile that is classical. Also, numerical models have obtained this. So we were able to do uniform internally heated convection in a tank. But what we were able to do a few years after was to have heterogeneous internally heated convection. Which this means, now here we are looking at our tank, the dimensions are in meters, 0.5 meters. We were able to construct 2 fluids, and the fluids here in yellow absorbs more of a microwave energy. So it simulates a fluid that is enriched in heat-producing elements. For this experiment, I show a lower fluid here in yellow that is slightly denser than the upper fluid and also has a higher heat production rate, in this case, 8.8 times. What do we see? Well, we see that when the convection starts, it starts again through cold downwellings of surface material, but these cold downwellings actually start to deform our layer with more internal heat production. So that this layer actually starts to get unstable, and you see this dome that is internally convecting. You see the errors here of the velocity. So it is internally convecting. And as time goes on, this layer, these domes may reach the surface or get close to the surface. And also here you see that there are some parts, for example, here where the colors is around the green color, which means that you have mixing of your material from layer 1 into material from layer 2. And what is also amazing is that in this type of experiments, because of technical conditions, we cannot have bottom heating, simply because you cannot heat the tank when you have all this stuff from a microwave. But what we see is that even if you don't have bottom heating, you can get plumes that reach the surface and are intrinsically hotter simply because they have some radiogenic elements. So all in all, I would like to say that these experiments tell us a lot about the role of internally heated material in terms of dynamics and in terms of long-term mixing. And I think that I would like to conclude here, just showing that I tried to show contributions from seismology, even if I know that I didn't show a lot, from geochemistry, like a little bit, and geodynamics, mainly focusing on present-day mantle convection and on the role of radiogenic heat producing elements. And what our experiments have shown is that the distribution of heat-producing elements in the Earth affects all the differentiation processes, but also mantle convection, mixing efficiency, and all in all, the whole thermal evolution of Earth. Okay, thank you.
Yeah, okay. Now I use the microphone because there are people from remote
Sure.
that have to listen. So we are ready now to get accept questions for you. Some questions from the audience. We start with the audience and then we
Yes.
ask the more.
There is a question there.
Okay, please.
Yes.
You will give.
Yeah.
Oh, sorry. I need to use the microphone. In the experiments, did you
Yes.
look at the heat transport scaling?
Yes.
And is it close to the sort of classical 1/3 Nusselt-Rayleigh scaling?
Now, this, okay, so the question is, relates to a relationship between the Nusselt number and the Rayleigh number through an exponent that we call beta. And generally, this beta is assumed to be 1/3, okay? Now, since our fluids are only weakly temperature-dependent viscosity, indeed, we find something similar to 1/3. But my point here is that the fact that we find 1/3 doesn't mean that in the Earth it is 1/3, because in the Earth you have temperature-dependent viscosities. Therefore, the cold subducting slabs are somewhat stronger, so you can spend some energy there in bending the plate. And this is what Uli Christensen show, that you can, and also others, Hager and so on, that you can decrease this beta factor to values around 0.1, which would probably be more realistic, and which would also help to better explain the thermal evolution of the Earth without moving back in time and ending up to a thermal catastrophe. And a thermal catastrophe means that you predict temperatures that are way too high, but all the mantle will be molten. So there is still quite a bit of work to do also on that field. But in our experiments, yes, we find this.
Please,
No, my question before
Yes.
concerning the homogeneity of the mantle
Yes.
is connected to the fact that we discussed this afternoon. Then when we try to extract from the geo-neutrinos flux
Yes.
the distribution of the radioactive nuclei in the mantle,
Yes.
one of the problems is that to know if the distribution is homogeneous or
Yes.
is, for instance, you say there is just a concentration in the border between the
Yes.
mantle and the core. And this is a big difference, of course, in for extracting the total radioactive nuclei presence, and then the production of heat of this decay. But it's clear, probably is for the moment there is no mean to understand which one of the two hypotheses is more correct.
Okay.
Probably, I don't know.
No, if you ask me what do I think about a hidden reservoir, well, personally, I like the idea that there is a hidden reservoir somewhere down there. Now, this hidden reservoir, if it is made of crust or a very, very ancient crust plus bombardment of meteorites that makes it denser and so on, then the crust would be enriched in incompatible elements. So the crust hypothesis would work. There are also other hypotheses which would be a leftover from a magma ocean. So we know that the Earth had a phase of magma ocean, so the whole mantle was molten, and then it started to crystallize. But where does it start to crystallize? Does it start to crystallize at the bottom and then moves up, or not? And if it is not, then we would have some areas really at the very bottom of the mantle where we could have some leftovers of magma ocean. And this leftover of magma ocean, since they are leftovers, would also be enriched in heat-producing elements, because these heat-producing elements are incompatible elements. So they stay in the liquid as much as they can. So I think that there are several ways to think that you could have something down there that is enriched. And this is interesting also for the coupling about the mantle and the core and heat transfer and so on. So it's linked to plenty of problematics. And honestly, we don't know. As a geophysicist, we don't know what's there. If you as a community could help us, this would be very good. Okay.
Okay, please.
The old idea to have a nuclear reactor in the core of the Earth is a completely good idea.
Nuclear reactor where?
In the core of the Earth.
In the core?
It's a
So
was a
you
good
would
idea maybe 30 years ago.
you would to put heat producing elements in the core?
No,
No.
a nuclear reactor in the core of the Earth. There was an old idea about to have a nuclear reactor. You're not.
Nuclear reactor in the Earth's
Yes.
core?
Yes.
Well, but
There is a
sorry,
an hypothesis, but I don't know.
I'm ignorant.
That in the core there are something similar to a nuclear reactor.
Ah.
This you
No, I'm sorry. Sorry. I hope to learn more today.
I have another question. Sorry. In the continental crust, okay,
Yes.
we go deep, 2 kilometers. I know that the maximum will be 20 kilometers in Siberia and some places.
Yeah.
Yes, 12.
No, but this
No,
borehole-
but on the other hand, you know that in the ocean, there are places where the material, the mantle material is visible.
Yeah,
So
yeah,
it's
there are some peridotites.
in that
yeah.
case, you succeeded to do the same measurement, go deep of 2 kilometers in that region directly in the mantle material.
Okay, so the question is, we know that some spreading ridges are very slow. So the velocity of spreading ridges and diverging plates is not constant, and some plates are very slow. And when you have very slow plates, sometimes you see that you don't form basalts. You don't even have energy enough to partially melt. And so we see peridotites that are at the ridges. So the question is, could we do a borehole and go down 2 kilometers and measure the heat flow and determine what is the heat flow at this kind of... I think this has never been done, also because nowadays boreholes are very expensive. And for example, the boreholes used by Claude Jopard in Canada are there because of mining research and so on. So they are already there. Set up a whole drill hole project. I mean, could be something. I don't know.
Other question, please.
I don't know, but I think you take the picture of a sort of the steady state. Is it possible to know the rate of this phenomena looking back, or even to predict something for the future?
You want to predict the future, or you want to go back in time correctly?
I'm asking if this is a steady state, or
Well, yes and no. I mean, when we are talking about heat flow, is the what is joule per second. So you have an energy per second, per unit time that is lost. And we know that roughly the Earth is cooling 100 degrees per billion years. So you go back in time 4 billion years and the Earth probably was 400 degrees hotter globally. Okay. So when we use this in order to predict what would happen, I think that one big question is, do we have enough energy to power the geodynamo? because you need some energy, some heat flow that is going out of the core in order to power the convective motions in the core, therefore generating a magnetic field. So the question is, would one day the convection in the core slow down or weaken the intensity of the magnetic fields? These, I think, are questions for the future. I don't know, then maybe also plate velocity would be affected in the futures, but slowly.
And the sun heating has no role in these processes.
No, I mean, the energy that arrives from the sun
Still
is much higher than what we produce in Earth, of course, but is high. But what do? You need energy to move the plates. You need energy to form the geomagnetic field. So you need energy from the inside, not from the surface. I'm sorry.
Do I see other questions here? Could you check, please, if there are questions from the people connected via Zoom? No, I have a question, a curiosity that when you take this measurement down in the ground, are you taking measurement also next to the volcanoes, or this will not be? Or you see, of course, you might see a very big difference if you go in the area of the volcanic areas, very close to the. No. Or these are not relevant for the.
Yeah, certainly they are done. But now you want to add another complexity, and is a complexity that we also have at spreading ridges, where you have hydrothermal circulations, which means that you have hot fluids that go all around. And this is difficult to integrate in our models, because when you do this game of calculating the temperature gradient and the rock thermal conductivity, then you calculate a heat flux that is associated to conduction of heat. Whereas in volcanoes and in some spreading ridges, you have fluid circulations, and there you had a component from advection of heat, because these fluids are moving. So you have to be somewhat careful at what you do. But of course, there are values on volcanoes, and generally these are very high values, of course. Yes, as expected. But do we need to integrate this here and so on? So it's another issue. Okay.
I think in principle we are in time. So if there are no other questions, we thank you very much for the very interesting discussion and presentation. And so we move to the next speaker, is Chris Davis from University of Leeds. Okay, please. Earth heat budget. Because I see better.
Okay, thank you very much for inviting me to talk to you today. I was asked to talk about the Earth's heat budget, but I'm going to sort of do it from the point of view of the Earth's core, since that's really where my expertise comes from. And I'm going to talk about things in the context of this thing called the new core paradox, which has sort of enlivened our interest in the heat budget of the deep Earth over the last decade. And hopefully that's going to sort of pull out some things relevant to the heat budget of the Earth as a whole. So, okay, that way, wicked. Okay, so when we're talking about the deep Earth, and in particularly the core, our primary observation, which was just mentioned in the discussion, is the evolution of the magnetic field. So when we're talking about very, very long time scales, so here sort of the age of the Earth, our primary observation is the strength of the magnetic field, and here it's plotted on the vertical axis as a virtual axial dipole moment. So that is the strength of the magnetic field normalizing out the natural variability you would get from a dipole magnetic field, so that you can compare across different latitudes. Present day is over here. Deep past is sort of on the right-hand side. The raw data is diamonds. Blue are sort of higher quality data, and then the black are means where there are greater than 10 data in a bin. So you can see that this sort of plot is a sort of huge sort of community effort. It represents decades of work, I guess. From my point of view, I really want to make two points about it. The first is that the magnetic field is quite old. So we have robust characterizations of the magnetic field back to 3.5 billion years. There's currently quite a bit of contention about whether the field was about the measurements shown by these pluses at sort of 4 billion years ago. And the other point to make, so the field is old, but also it seems to have been continuously generated. There aren't any obvious gaps or holes in this record. The gaps are sort of more because we don't have high fidelity rocks of the right age, rather than because anyone believes the magnetic field was not being generated. So the sort of first order problem is to explain how we generated a long-lived magnetic field sort of for the last 3.5 billion years. And what does this tell us about the deep interior of the Earth? So to start with, sort of where we can probably all agree, is that this magnetic field is the product of a hydromagnetic dynamo. This is a dynamo process that's operating in the liquid core of the Earth. So here's the solid inner core, here's the liquid outer core, the mantle would be surrounding it. And essentially, what the hydromagnetic dynamo is doing is taking kinetic energy from a moving fluid and converting it into magnetic energy. And the way it does that is, the flow is rotationally constrained. The flow will twist and stretch magnetic field lines. But for our purpose here of understanding very long-term variations of the deep Earth, we don't need to worry about the details. All we need to know is that there is a process, a dynamo process, that can convert kinetic energy into magnetic energy. And our question becomes, where does the kinetic energy come from? And the classical picture is that it's ultimately derived from the heat that is being extracted from the core by the mantle. So the mantle pulls heat out of the core, that sets up thermal and chemical buoyancy forces that drive the motion that maintain the field. And as we have already seen, thankfully, the previous talk has set up my talk very, very nicely. This core mantle boundary heat flow is part of the wider heat budget. So we have estimates for the total amount of heat leaving the Earth, 46 plus or minus 3 of the estimates I've chosen here. And we have independent ways of estimating the amount of heat production in the mantle and the lithosphere. And the real question becomes, how do you estimate what's left over? The heat that is in the core and the secular cooling of the mantle. And really, one of the things that the paleomagnetic observations can help us with is to figure out this piece and to hopefully then reduce some of the uncertainties on the other pieces. You can see that the uncertainties are incredibly large depending on how you play this game of where the heat is stored. So let's pick the slide up. So the dynamo is powered by cooling, the core mantle boundary heat flow, and this can hopefully help us constrain one of the sort of 4 primary aspects of the Earth's heat budget. But we also get some other information because this cooling leads to growth of the inner core, of the solid inner core. So this is sort of a schematic of how this process works. Temperature on the vertical axis, radius on the horizontal. The dashed black line is showing the melting point of the liquid iron alloy. So this is the melting point of pure iron as a function of essentially pressure, but then depressed because of the presence of some light impurities. In this case, it's oxygen and silicon. And what happens is we start some time ago, in this case, 1 billion years, with this blue line. Technically speaking, this is an adiabatic temperature profile. The core is incredibly well mixed. So on timescales of millions of years, it's expected that the departures from an adiabat will be very, very small. So we start from this hot core. The blue curve is everywhere above the melting point. The core is entirely liquid, and the mantle keeps extracting heat from the top of the core. And eventually, you can see as we go from green to red, we intersect the melting point, at the center of the Earth, which is why the inner core is growing outwards, and the inner core will slowly grow to its present day radius of 1,221 kilometers. So the cooling and the cooling rate of the core constrain the growth of the inner core, and we have a constraint from present day seismology, which is that any model of our evolution of the Earth has to match the radius of the inner core. Okay. So how do we play this game? We're on these very long time scales. We're not solving the Navier-Stokes equation. We're not doing very complicated dynamics. We're doing what are sort of called thermal history models, if you like. The very similar game is played with the mantle, where essentially you just add up all the energy in the system. You take, if we're looking at the core in isolation, the amount of heat coming out of the core, QCMB, and we relate it to all the heat that's inside the core. This is just the first law of thermodynamics. And when we haven't got an inner core, things are very simple, because the only heat that we can have in the core is QS, so this is the secular cooling, the core's analog of the mantle secular cooling, and QR, which is the radiogenic heating due to any radiogenic elements that might have got into the core. When you have the inner core is a real bonus, not just because it's there as a constraint on our models, but because it energetically very much helps the dynamo. It provides two sources of power. So QL is the latent heat that is released on the phase change. So as the phase changes from solid to liquid, heat is released. That heat is released at the bottom. So that's helping to drive thermal buoyancy. But what's even better is that we know from seismology that the liquid outer core is less dense than the solid, and that density deficit is too big to be explained by the phase change alone. So the light elements must partition preferentially into the liquid, and indeed atomic scale simulations bear out that is exactly what they do. Atoms like oxygen don't fit preferentially into the solid lattice, they're expelled from the solid and they're left in the liquid. And so when you leave a bunch of light stuff at the bottom of the liquid core, it's going to rise. It turns out that this process is incredibly efficient at mixing the core. This, as you'll see though, this the eagle-eyed of you will have noticed that this energy budget tells you nothing about the magnetic field. There's no mention of a magnetic field anywhere in here, and that is because magnetic energy is converted to heat inside the core, just like viscous friction is converted to heat inside the core. It doesn't appear in the global energy budget, but you can get at it if you consider the entropy where all the dissipative processes emerge and the cores. Oh, and I should say that the nice thing about the energy budget is that with the exception of the radiogenic heating, everything can be related to the core's cooling rate, dTc by dtime. A is an integral over core properties. We can talk about it later if you want to. I'm not going to mention it very much now. But when you consider the entropy budget, every heat source gets its corresponding entropy term, so that there's an S, an L, a C, and an R. And again, all bar the radiogenic heating, you can relate these to the cooling rate of the core, and you get two positive definite terms on the left-hand side. One is EA, this is the entropy due to thermal conduction, and the thing that we actually want, EJ, is the entropy produced by the dynamo process. So you could imagine this to be the total work that was required to be done by the fluid in order to produce the magnetic field B. And there's a prescription here that if we knew the CMB heat flow, we could obtain that from mantle convection, and we knew the amount of radiogenic heating, then we can figure out the cooling rate, get it to figure out this EJ. EJ needs to be positive for dynamo action. It gives us a constraint on the dynamo process over time. The thing that's really reinvigorated the debate here is this thing, the thermal conduction, because our estimates of the thermal conductivity of the core have changed quite a bit over time. And I'm going to talk about that quite a bit. The classical model of the core initially starts by ignoring the radiogenic heating for reasons that we're going to discuss. And of course, I'm going to reinstate it at some point. But the most basic model is simply cooling. You cool the core until you freeze the inner core, then you get latent heat and gravitational energy to power the modern dynamo. And we have two primary constraints from the core side. Our constraint of continuous dynamo action mathematically arises that EJ needs to be greater than 0 for the whole of time, and we need to match the present day inner core size. Okay, So the thermal conductivity, this has really invigorated a lot of debate over the last 10 years. This is a plot here of the thermal conductivity K on the vertical axis, and its temperature and pressure dependence here. And there's a whole bunch of studies, as you can see, and the ones that are circled here are the ones that are actually at the conditions of Earth's core mantle boundary. So 4,000 Kelvin, 135 gigapascals. And you'll see that these are quite a bit higher than some of the estimates that are at lower pressure and temperature. And it turns out that this really affects what you infer from the Earth, about the Earth, based on the previous model. There's a lot of detail in this, and indeed, you often see in the literature people say that the thermal conductivity of the core is unknown, my argument is that it's not, but the devil is in the details here. It depends on whether you did a direct determination of the thermal conductivity or whether you tried to infer it from the Wiedemann-Franz law using an electrical resistivity. It depends on whether you did an experiment on a solid or a liquid. It depends on whether your calculation has electron-electron scattering and so forth, okay? And when people extrapolate in different ways to core mantle boundary conditions, extrapolate all of this, there will inevitably be different results. But the point is that whether you use a low thermal conductivity or a high thermal conductivity really matters in terms of what you learn about the Earth. And this is a summary of that. And I have only got one table in this slide, in this presentation as well. But the table is sort of supposed to be summarizing the plot over here. So broadly speaking, I've broken this up into two scenarios for the evolution of the core, one based on low thermal conductivity and one based on high. And it's important here to say that what we've done is to just choose the core mantle boundary heat flow. Don't worry about the mantle, just choose the core mantle boundary heat flow in a prescribed way. And what you've got here is some results for low thermal conductivity and some results for high thermal conductivity. The different symbols essentially represent different ways of calculating these integrals A, B, and C. They account for differences that arise from the core's composition, its thermal state, and so forth. Gives you an idea of the uncertainty in the calculation. And what you're looking at is the ancient core temperature on the vertical and the inner core age on the horizontal. So when the conductivity is low, when we take classical estimates in the literature, you'll get an inner core of about 1 billion years old. So everyone agrees the inner core is not a primordial feature of the Earth. 1 billion years is what you'll see in the literature. When you go to low thermal conductivity, your inner core becomes an awful lot younger, 500 million years. And essentially what's happened here is that in order to maintain the same dynamo, i.e. to produce the same set of paleomagnetic observations, you've had to cool the core faster, which means that it had to start out hotter. If it had to start out hotter, its temperature at early times is much higher. And the implication is that at early times, if the core had a high thermal conductivity, it would have been very hot, much hotter than the lower mantle solidus. And so there could well have been this sort of hypothesized basal magma ocean. So that's the sort of the basics of why the conductivity matters. I just want to point out that if you do take all of these conductivity estimates and you extrapolate them in a consistent way, i.e. you use the same set of numbers to extrapolate them, you actually get reasonable consistency. You get some outliers, but you get a bunch of conductivities in the range of 70 to 100 watts per meter per Kelvin, which is about double the value that people were using prior to 2012. Also, if you do direct calculations of the thermal conductivity on a computer, so this is sort of the black dash, and you compare these to experimental values at sort of relatively high pressure and temperature, you do get quantitative agreement within the uncertainties. So there is support for considering this high conductivity scenario for the evolution of the Earth, and that is the scenario that I'm going to consider. Okay. So an example of what happens when you have high core conductivity and you now couple the evolution of the core to the evolution of the mantle. This is, I guess, what we call a classical mantle evolution model. You've got two boundary layers that are, mediating the heat flow. There's a sort of normal amount of radiogenic heating in the mantle. And what happens is, if you've got a low conductivity, so the main things to look at, you've got heat flow and entropy here. The left-hand side is low conductivity. The surface heat flow is in black. The core mantle boundary heat flow is in blue. And the main output is this thing, the ohmic dissipation. In this case, it's positive for the whole of time, and you get this big kick when the inner core comes in, because you get the gravitational energy and the latent heat. In the same case with high core conductivity, this whole grey region here is predicted to have no dynamo action, which is completely inconsistent with paleomagnetism. So this is the sort of the basic problem that is that arises, and it brings me to what is the new core paradox. Well, the new core paradox is precisely this problem, that we have two observations of the deep Earth that we believe in. One is the present day size of the inner core, and the other is the continuous field generation of the magnetic field. But if you take a classical model of the thermal evolution of the core, you really, really struggle to match these two constraints. So this idea of it being a paradox was coined by Peter Olson, of just how do you reconcile the model that everyone believes in with the observations that everyone believes in. Okay. And really what I'm going to do for the remainder of this talk is present 4 different ways to resolve the new core paradox. Okay, so the first one, what you're looking at here is a set of coupled, so what we're doing here is we're solving the equations that I just showed for the evolution, the thermal evolution of the core. There's a similar set of equations for the thermal evolution of the mantle. They're coupled at the core mantle boundary through the heat flow. The core sets the temperature, the mantle sets the heat flow, but of course then the mantle will respond to change the core's temperature and so on and so forth. What you're looking at here on the vertical axis of all 4 of these plots is the ratio of lower to upper mantle viscosity. So it turns out that this is that the viscosity of the mantle is incredibly important, as you might gather. It's also not terribly well known. And on the horizontal axes are different variables that were varied from a nominal set of parameters. Okay, so the first, and what you're actually looking at is this thing EJ, the entropy for the dynamo, and you're looking at it at a specific time just before the inner core nucleates. And the reason for that is when you look at these plots, the point where this entropy production is always the lowest is right before you nucleate the inner core. So this is the key point. If your model's going to fail, or your model prediction is going to fail, it's going to fail right before the inner core forms. So it's worth looking there. Okay, so the dashed line shows the sort of parameter combinations that give you the right inner core radius. The solid line delineates positive entropy production, so like the sort of greeny reddy, from the negative entropy production, and you want to be on the red side of it. So what you need from the top plot is you need your thermal conductivity to be less than about 30. So you need to be on the sort of the left-hand side of this plot, which is no good if the mineral physicists are telling us that the conductivity is at least double that. The other way you can try and get around this is by sort of changing the thermal structure of the core. So if you look in the literature, melting point of the inner core boundary, somewhere between about 5,300 and 5,900 Kelvin. If you make it on the very low end of those estimates, you can get to a point where you've almost got a single solution. This is really tuning the parameters. You have to get things just right, but you can almost do it if you make the melting point very, very low of the core. The solution that definitely works, and the one that geophysicists have loved over the years, is to have some potassium-40 in the core. Potassium-40 works because, as you saw from the equations, it means you can cool the core more slowly. You just got an extra heat source. And indeed here, if you have more than about 2 terawatts of potassium-40 in the core, then your life's good. And you can keep the dynamo running. You can match the present day radius of the inner core, no problem. It turns out actually that the Urey ratio was mentioned before, and I guess I haven't cast things here in terms of the Urey ratio, but what we have done is varied the amount of present day mantle radioactivity with the heat flow being a part of the solution. And it turns out that these particular solutions aren't terribly dependent on the amount of radiogenic heat production in the mantle. And that is because of the feedback through the mantle viscosity. So you put more radiogenic elements in the mantle, it keeps the mantle hotter, but that decreases the viscosity, which pulls more heat out of the core. And you end up, from the core's point of view, you end up sort of back where you started. But there are two solutions implied by this. Okay, so one way out of this whole thing that was known 20 years ago is you just put a load of potassium-40 in the core and your job's a good one. The problem, as has already been mentioned, I've taken a slightly different image from the same paper, but when you look at the partitioning of potassium-40 between silicate melt and the core, then you find that by the present day, the amount of heat that's being produced is a terawatt or less, and we need at least 2 in order to match the constraints provided by paleomagnetism and seismology. So it's an appealing solution, and if someone can find a way of getting more potassium-40 into the core, then the whole thing is solved. But according to partitioning studies, this is not viable. Now, we also have this tuned solution, and here is an example of a tuned solution. Okay, the entropy production here comes down, 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 down. It's almost zero, but no, it's okay because the inner core comes in, saves the day, and Earth stops. And Earth doesn't end up like Mars, and it ends up like Earth. You get a very, very dramatic change in the core mantle boundary heat flow. And in order to make the solution work, you have to start the Earth off hot, and you have to have a low melting point. And I mean, this is a solution that I am partly responsible for finding, but I don't find it particularly compelling for 2 reasons. One is that if we look at the melting point of iron, this is a study by Anzolini and co-workers. It's sort of it's black line here is the melting point of pure iron. So we can depress that by a bit, depending on how much, well, quite a lot actually. You can depress it by probably a few hundred Kelvin, depending on what's in the core. But the value that we've used is here, which is really pretty low by anyone's estimation. The other problem, of course, is that this solution is just inherently unappealing because all of the parameters have had to be tuned. There's just something that you know people don't like about the Earth being a needle in a haystack. So it would be nice to perhaps look for alternative solutions, and indeed there are 2 more. So solution 3. Precipitation of oxides. So what people realized once the new core paradox had come along was, wouldn't it be great if we could just have something like inner core growth, but for the whole of time? Because the compositional, the entropy we get from compositional buoyancy is incredibly efficient. It doesn't suffer a sort of Carnot penalty like the thermal contributions. So people started looking at magnesium, and the idea is, well, if you could get magnesium into the core, which is a whole other talk, but imagining that you could get it into the core, perhaps during a high temperature core formation event, would it then precipitate out of solution as magnesium oxide? And what you can do is you can figure out the equilibrium concentration of magnesium. So this is and then you can compare it to what the concentration might be in the core. And so when the core's concentration exceeds the equilibrium concentration, the core has got too much magnesium in the liquid. It's energetically now more favorable to precipitate the magnesium out of the liquid as magnesium oxide. So in my badly drawn cartoon, the magnesium oxide is now the little circles, and what you've left behind is a fluid that is enriched in iron compared to the rest of the core, because you've stripped the light stuff out. And of course, because it's a liquid and you've left this dense liquid at the top, Rayleigh-Taylor instability will very, very quickly mix everything. So this is a bit like inner core growth, but in principle, it could happen for the whole of time. In this particular model, it starts happening at 5,200 Kelvin. Well, the Earth's present day temperature at the CMB is 4,000 Kelvin, so this could have been happening for quite a while. Right, and loads of people have looked at this. So you take your classical model of core evolution, which is the one I've already shown you, and you add in a new term, QP, the power due to precipitation. And again, it depends on the cooling rate. And so you can just play exactly the same game, but now this QP, the precipitation, is playing just an analogous role to the gravitational energy QC, but over the whole of time. What you need to do is you need to figure out the temperature when precipitation starts, and you need to figure out how much power you get, which is proportional to sort of how much the mass fraction of stuff you precipitate per unit temperature change. And this is a game that we played. We looked at a whole load of stuff. These are different combinations of reactions, whether they're dissolution reactions, heat exchange reactions, and so forth. You have to prescribe how much the weight percents of stuff on the mantle side if you're trying to figure out what's on the core side and so forth. And the point is, really, the thing I want you to take home is that you can get a huge range of estimates, right? The onset time for precipitation of magnesium or of silicon can be over here. So, i.e. at a lower temperature than the present day temperature of the core, meaning it hasn't yet started. Likewise, precipitation can start at 6,000 Kelvin, i.e. when the core formed, potentially. And likewise, you can get quite low precipitation rates all the way up to quite high ones, okay? So this mechanism, in principle, is perfect. It works really, really well if you can put the numbers into it. So anyway, things are uncertain. But I just want to show you one example for silicon, okay? So this is precipitation of SiO2. We had a little bit of a go at this. My colleagues at UCL, Dario Alfi and Monica Pozzo, used ab initio quantum mechanics to calculate chemical potentials for silicon in silicate melts and iron oxygen silicon liquid. Those are the diamonds. We combine them with a whole load of experimental data to produce a thermodynamic model that would then allow us to figure out when the precipitation starts and how much power you get out of it. This is an example. So there's two calculations here, one that has no precipitation and one that has precipitation. So the blue is the precipitation. And you can see that, really the main point is the entropy down here, where the one with no precipitation fails, as we'd expect. The one with precipitation is happy, carries on generating a magnetic field for the whole of time. And that gives you a whole sequence of models that sort of fit your constraints. So this is sort of the same temperature a long time ago versus in a core age plot that I showed before. The precipitation, you've got various different models depending on whether the core started with a lot of oxygen or a little amount of oxygen. But the point is you get two groupings, and in both of them, the inner core tends to be older than if you didn't have precipitation. And that's because precipitation is sort of doing what the radiogenic heating is doing in a way. It's just letting you cool slower. Okay. So you can now bring the inner core age back to about 1 billion years. And the core is colder. It's colder than with precipitation because you're cooling. It's worth saying, though, that if you take a sort of upper bound on the lower mantle solidus, a lot of these models are still predicting that a long time ago, the core was very, very hot. And this raises the possibility of one final solution that we've sort of touched on, which is the hidden reservoir. But here it's a different hidden reservoir. Well, it is and it isn't, because you've already mentioned the basal magma ocean. And indeed, this is a very nice solution because it's consistent with the results. All of these results have assumed that the mantle is solid everywhere. But the temperature is so high at early times that there is good reason to believe that, in fact, the lower mantle is not solid. So what we can perhaps do is take our simple classical model of the core and replace it with something that looks a little bit like this. Okay, so what you now have is a sort of 3-layer Earth. So you have the core, which we're treating as we were before, those set of equations up there. You have a solid mantle up here, which you're sort of treating as you were before. And you have this thing in the middle, the basal magma ocean. The basal magma ocean is somewhat enigmatic. I mean, as was explained before, it comes about because in principle, the melting curve of the silicate can have curvature, and that can allow the freezing to start from the center. And then what happens is FeO partitions into the magma ocean, keeps it dense, keeps depressing its melting point, so that the basal magma ocean remains there. I guess what's interesting perhaps for this audience is that in this particular model of Labrosse, about 1/3 to 1/4 of the Earth's entire radiogenic inventory is sequestered into this magma ocean, which we have implemented because that was his model. There's latent heat that is being released in this magma ocean because it's sort of supposed to be only partially molten. And also, because you've got a magma ocean now above the core, you can actually transfer mass quite easily between the core and the mantle. And in particular, it's very favorable for FeO to want to go into the core. So there's an additional heat term representing this extraction process. And you can get a solution that works. And it works because EJ here, the entropy production, is positive for the whole of time, no problem. What's the point of the basal magma ocean? What the basal magma ocean does in this particular solution is it keeps the core's cooling rate low. Solid state mantle convection, at least in the classical parameterization, will make the core cool really fast. And you can see it here if I compare my old solution of the heat flow, QCMB, well, Q surface is here. The heat flow here in the basal magma ocean case is a lot lower. Here's the heat flow from the core. And in fact, the core's heating up for the first bit of time. And that is because the latent heat and the radiogenic heat inside the magma ocean is drastically suppressing the heat flow out of the core. Okay. But then what happens is the magma ocean becomes negligibly thin. Solid state mantle convection begins, and you start at around about here, and you start getting a sort of drastic change in the energy and entropy budgets of the core. So this solution requires no radiogenic heating in the core. It requires no precipitation. It requires this model of the basal magma ocean, and we could sort of argue all day about the details of how that is done. How much time am I over time? 3 minutes. Oh, I'm going to say one more thing then. So since I've got my 3 minutes, I'm going to just say a little bit about what the paleomagnetism requires, because I haven't actually specifically linked any of this to paleomagnetism. And that's because that requires a little bit more theoretical machinery to relate this thing EJ to an actual field strength. It requires understanding the balance of forces in the core. Okay. But assuming that we can do that, right, then essentially what we can do is take all of our thermal histories, take all of our EJs, our dynamo entropies, and convert them into field strengths, and then look for the solutions that best match the paleomagnetism. And that's one of the solutions is here. Okay, this is a solution that does reasonably well. Here, I've actually parameterized the mantle heat flow using this very, very simple equation. And this is to try and look for essentially what paleomagnetism would like the CMB heat flow to do if it had its way. And what it wants is a CMB heat flow that is about somewhere between 11 to 16 terawatts at the present day and rises relatively slowly over time. And I should, and yeah, that's it. And it rises to about 17 to 22 terawatts over time, which is completely incompatible with the classical model of mantle cooling, but something like Koronaga's model of sort of dehydration stiffening, you can get this sort of variation. So anyway, I'm going to end with these 4 potential solutions to the new core paradox. 2 terawatts of, so there's 4 solutions that I know of. 2 terawatts of radiogenic heating in the core, but geochemistry doesn't like that. You can make the initial core very hot, so 6,500 Kelvin, and you can make the melting point of the core very low. But this is a sort of tuned solution. You really have to look quite hard for these parameters. You can invoke a basal magma ocean. The problem being here that there's a lot of physics in the basal magma ocean that is poorly understood. Or you can have precipitation of oxides, which really, really works, but you've got this challenge of figuring out how much power you get for the precipitation of an individual oxide. Thank you.
Thank you very much. Also, this talk was very interesting and stimulating. So we have time for questions now. Please.
But I have a question. Okay. So you show that you have a chemical layer, your orange color, and do you have any idea of a composition? And do you have any idea if this layer could be seen by seismologists? and could have an effect of how we register variations of a magnetic field today and so on. So how do we see this layer, if we can?
Good question. Could I have the slides again? Then I could show it.
Yeah.
Ah, this one. Yeah. So actually, the part of the purpose of doing this was to see if you can explain the stratified layer at the top of the core that is seen from seismology. So these multiply reflected waves at the top of the core suggests that there is an anomalous region that is about 1 to 2% variation in the P wave velocity. And the idea here is that the sort of partitioning studies suggest that the oxygen will go into the core as FeO, and it will be light, so it will sit at the top of the core. And so that's sort of what's happening here, is that oxygen is being extracted from the lower mantle and forming this stably stratified layer. And I might have a spare slide that shows how it does. Here. So this is the Brunt-Weisler period of the layer that we get. So these are our layers, and these are the inferences. And the main one from seismology is this one, Helfrich and Kaneshima. And so we're a little bit off. Actually, ironically, this layer is too strongly stratified, which means there's too much FeO in it. But not, I mean, by a little bit. But we also tried it with just a purely thermal layer, and then you're not strongly stratified enough. So the thermal layer never works. The chemical layer is a bit more challenging.
Do we have questions from remote? No. Please.
Thank you for the presentation. It was very nice. I would have a lot of curiosities. Maybe I will ask you later. Just one question. You mentioned the solution where you fit the parameters, you tune the parameters.
Yes.
And it seems to me that you are not very in favor of this hypothesis. Is this because the tune values of those parameters differ a lot from experimental measurements or things like that? Or in that case, I could also think that there are some scale effects. I mean, if you take measurements on samples in a laboratory, things could be much different from what happens at a very large scale length.
Yeah, I think what makes me nervous is that all these results come with some uncertainty. And, you know, you would like to think that your solution was robust within the uncertainty on the measurement. And I talked to my colleague Dario, because he's done a lot of work on the melting point of the core. And he sort of said to me, the uncertainty on his melting point for pure iron is about 300 Kelvin. So you then add in the light impurities. We don't know what those are, and we don't know how much they depress the melting point. So the uncertainty is at least 300 Kelvin. And that solution is not robust to a 300 Kelvin change. And that's what makes me nervous about it. It's hard to just say that is the exact melting point. On the other hand, it is consistent with, there was a particular study that argued for a very low solidus of pyrrolite. The Japanese group argued that the solidus of pyrrolite is about 3,500 Kelvin, which would give you a CMB temperature of around about that amount. If you take an adiabat and project that back to the inner core boundary, it's about 5,300 Kelvin or something, which is fine.
Please.
Thank you for this talk. I'm a particle physicist, and I'm performing these days an experiment to measure with high precision, plus or minus 1%, the rate of cosmic rays as a function of latitude, from about 50 degrees up to 82 degrees north. Mm-hmm. So we see the effect of the magnetic field of the Earth. And my question is, apart from the experimental input from the measurements of the Earth's magnetic field, what other really stringent experimental measurement can constrain the models? Temperature, radiation, apart from the magnetic field?
Observational constraints. So I mean, well, okay, I guess we have. So I mean, we have the seismological constraint on the basic 1D structure of the core at the moment. That's a pretty stringent constraint. As you say, the magnetic field is a pretty stringent constraint. What else could help that's actually reasonable? Seismology gives us a stable layer, but it's not, it doesn't matter that much. I'm gonna have to think about it. Yeah, I mean, of course, we have things like the nutations. So the nutations tell you, I mean, once you've subtracted the oceans, the atmosphere, and all these other things, you know, they will tell you how much angular momentum is being exchanged between the fluid core, solid core, and mantle, which in principle, again, it allows you to back out either something about the viscosity or about the magnetic field strength at the core mantle boundary or at the inner core boundary. So that's another constraint.
So since I don't see other questions, it's time for my question now. So concerning this model, this basal magna ocean, what is your, how do you fix the radius of this, the thickness of this part, and how much could be affected by the composition of this?
Right. So I mean, we follow pretty closely this study by Labrosse. It's a sort of very influential paper in Nature in about 2007. I mean, the way we did it was we take the melting curve for silicate melt from Lars Dixrud, compare it to a sort of a notional magma ocean adiabat, and then the intersection point is what defines the initial thickness of the layer. And then over time, what happens is the layer shrinks, and you calculate how much it shrinks by. It's constrained by the fact that the layer is constrained to stay near the liquidus. And what's happening in Labrosse's model is that FEO is continually being partitioned in from the solid. So that sort of constrains its compositional evolution. There's like a fixed partitioning at the top.
Okay.
But in our model, we additionally allow the FEO to go into the core because it's absolutely clear that that's what it wants to do.
Okay, very interesting. So I don't see, I think we got to the coffee break time. Thank you very much. And I thank also the
just a moment, excuse me, just a moment. I would like just to say, to inform the speakers that the slides will be posted on the site of the Italian Physical Society. In addition, if by chance we have something written connected with the matter of your talk, in that case, please send to us, because we can send to the people registered on this symposium. Thanks.
Okay. Thanks. So we will send the address for the slide. Okay.
No, they can send also online on.
Yes, we put this, but we also we send a reminder to the speaker. Okay, so I like to thank you very much again for this very nice first session. And so we go to the coffee break. Thank you very much.
So the next speaker is Jacques Marteau, Université Claude Bernard, Lyon. And Jacques will speak us about muon tomography and volcano study. Here in Italy, we're very interested in having a lot of volcanoes.
Okay. Very good. So there is just testing this. Okay, very good. So first, let me thank the organizer for the invitation and for giving me the opportunity to represent now a community which is getting larger and larger. In, let's say 15 years ago, when we initiated this type of physics in France, we were really the first. And we were among the first at the international level. And now there is really a large community of what we call the muographers. And there is also a large community here in Italy, because this will be linked to the volcano case. And actually, as you know, there are quite a lot of volcanoes in Italy of interest. So what is the idea of the muography? So the idea is that we will take advantage of the cosmic ray muons, which are created naturally in the atmosphere. Okay, let's take a look at the sketch, which is on the top left here. And we will look at the changes on the muon trajectories, which may be induced by the object of interest. And those changes may manifest themselves either by the absorption of the particle or by the deviation of the particle. Okay, so basically the muography principle are just the one which are exposed here in the top left sketch. So what is really interesting in this field is that this is a field which is mixing the competencies of two different communities. One is the community of the particle physicists, and the second one is the community of the geophysicists. And actually, the particle physicists, they are really good in making simulations, building detectors, and getting collection of data out of these activities. And this is what, in terms of the geophysics vocabulary, we call the direct problem. How we get the data from the absorption of the muon crossing a volcano, for example. Then, once you get the data, of course, you're just at the beginning of your job, because detecting muons nowadays is not the big deal. Okay, muons has been discovered in the 30s of previous century. It's almost 1 century that we know how to detect muons, and this is, of course, not the difficult part of the job. What is the difficult part of the job is, once you get the data, how you get back to the mass distribution within the targets that has been crossed by those muons. And this is what the geophysicists call the inverse problem. And this is, of course, where the difficulty is. And we will see that not only the muography enables you to make structural imaging, okay, but it also allows you, to a certain extent, to follow dynamically what are the changes within your targets. And this is an important application for the monitoring aspect. In the previous talk, we heard of the hydrothermal system and so on and so forth. We spoke of this hydrothermal system in the volcanoes. And you will see that this is really an application which is worth pursuing with the muons. So I will give you some insights on all that stuff, especially in the context of the volcanoes. So, direct problems. I will make a long story very short. We know that there are particles which are generated within the atmosphere. Okay, there are primary cascades initiated on the top layers of the atmosphere. And then there are all those showers of particles which go down from the top of the atmosphere to the ground level. Those particles, showers, they are rich into light particles, light hadrons, for those who are not familiar with this, which are called pions. Those pions decay and give mostly muons and most elusive neutrinos, but neutrinos will be addressed in the next talks. And so muons are produced, and the rough number that everyone has to keep in mind is that this is 1 muon per square centimeter per minute at the ground level. Okay, so this fixes the scale of the statistics that you have to fight with in order to make images of your structure, whatever this is. This is something that is quite well known, okay? As I told before, this is almost 1 century that we discovered the muons, so we're not now making huge discoveries. But as you will see, when you want to go into precise imaging of large structures, then perhaps the knowledge that we have on the cosmic ray muon flux all over the Earth, and also the dependencies of this flux to the environmental parameters, is not enough. and we will see this in detail before. But okay, to, let's say, first order, we know the flux, we know the spectrum of the flux, and we can, let's say, make first images with this. So really, for those who are not familiar with this, but who like Sheldon Cooper, then this is the Big Bang perspective of the muon. Muon is one of the happy few of our 12 elementary particle, okay, and this is a lepton. This is a kind of big electron, which mass is something like 200 times larger than the electron mass, and this is precisely the property that allows him to cross matter over hundreds of meters up to kilometers before being completely absorbed. And this is actually what we are exploiting in muography. So here in the central sketch here, you see the digital elevation model of a volcano that I will speak a lot about. This is the Soufrière of Guadeloupe in the Antilles, which is one of the 3 active volcanoes under the surveillance in France. Okay, there is Soufrière, there is the Montagne Pelée in Martinique, and there is, of course, the Piton de la Fournaise in Réunion. So this is one of the bad guys that we have, and actually I will speak a little bit in detail more later, but this is the digital elevation model of the volcano in gray. In red, you see the trajectory of the muons, which are produced in the atmosphere and which are able to reach a detector, which is a simple tracker here. So I will show you some picture before, but you see that the detector, which is typically a cubic meter detector, because this is a simple apparatus that you want to build on the field, and the field here is just in the middle of nowhere. You have no power source, you have no Wi-Fi, you have no technical support, you have no roads. So you have to bring your detector on the back of a man, and of course, a man as strong as he is cannot carry on 2 large objects. So this is typically the type of apparatus that is used on the field, where field means a real field, not a field close to a road where you can have everything you want. And so you see that some of the trajectories of the muons cross the volume, the inner volume of the upper dome, of course, and some are directly coming from the open sky. So those open sky muons, which are not crossing any matter, you can use them to monitor the relative variation of the flux. And those who cross the volume of the dome, you will use to determine the absorption. And actually, the parameters you are sensitive to is what we call the opacity, which is the integral of the density along the trajectory of the particle. Okay? And so all the game for the inverse problem is to go from this observed absorption to the density distribution within the target. And this is the type of maps that we get here on the left. This is the type of maps that we get from the active dome of the Soufrière, where the blue zones are the negative density anomalies, so let's say the cavities, and where the red and the brown zones are the one which are really dense, meaning here. So what you see here is that there are really heterogeneous dome for this volcano. The most active zone here corresponds to the what is called the south crater, where you see vents coming out at more than 100 kilometers per hour over here. And there is another large cavity here, which was known in the ancient time as the Spallanzani cavity, and which was explored by the people who like to make speleology, but now is closed because after the last eruption, the entrance of this cavity was not accessible anymore. So this is typically the basics of the muography. The type of tracker that we were using to do these experiments is a tracker which is really something that you can find in the school, and this is a scintillator-based tracker. The reason why we chose this is because this is the most robust that we know. Okay, this is everything about plastic. basically. So you can dive this into water if you want. And on a volcano such as the Soufrière, where you have 10 meters rain per year, this is something that is really useful to have something that you can run in any conditions that you can encounter. So for us, it was out of questions to have gas, to have high voltage, to have whatever we want. Of course, we know that this is not the smartest detector in the world, but this is at least the most robust and adapted to all the harsh conditions. Of course, muography had been and made the buzz, a huge buzz some years ago with the discovery of this new void in the Big Pyramid. So this is just to show that muography nowadays, and I will conclude on this afterwards, is applied to many fields. Actually, this is one of the first applications ever proposed by Alvarez et al. In the 70s of the previous century, to try to use this muography and this muon absorption to focus and to discover new voids. So this is something that is actually going on. There is this new void that has been discovered, discovered by the use of 3 different techniques, actually that I illustrate here. You can see on the bottom left nuclear emulsions that were used in the previous photographies. Micromegas, which is a gaseous detector that is quite fine, and which, so those 2 guys have the advantages of getting high spatial and angular resolution. And scintillators, of course, were also used in the pyramid. From now on, I will focus on the volcano imaging, because there are a lot of advantages of using muography to make this volcano imaging. First, you make an image from remote. So when you have an active dome, this is something, of course, which is important because you don't expose anybody to take a measurement on site. Second, you can, with a single point of view, have the full image of a large dome. Okay, it depends on how large, of course, because you could be limited. And here in Italy, there is a large collaboration called Muraves, who is focused on the Vesuvio, okay, in Naples. But Vesuvio is such a large detector that they have to put station all around the dome, because you cannot embrace the full dome in a single point of view. Or if you do so, then you don't have the resolution to say whatever interesting you wanted. And as I will show afterwards, you can follow what is going on inside by making a very interesting monitoring of the hydrothermal system when there is one. Okay, so there are now many open questions in volcanology. I'm not a geophysicist, so I will not run into all of them, but this is something that, of course, may be discussed by the confrontation of the 2 communities in such a symposium like this one. Just to give you an overview of the use cases, at least that we do in our small business of muography, we have application in geoscience, in archaeology, and nowadays in industrial controls more and more. Because in all the large industrial infrastructures, you will find big containers, big tanks, big pipes, big whatever, where the industrial do not know exactly what is the contents of the tank of the container, and they cannot approach, they cannot open it, they cannot stop the production, etc., etc., etc. Always the same constraints, and they want remote imaging device in order to look what is inside those tanks and containers and whatever. And there are a lot and more requests from their side, on our side, in order to perform this, at least first proof of concept measurements and then imaging of their large structure. You see in the nuclear power plants in France, for instance, we got some requests, civil engineering, tunnel boring machine, prospection, mining, whatever. In the archaeology, of course, the case of the pyramid has been made famous by the Scan Pyramid collaboration, but we have also made some trials on a much more difficult situation where you have a small tumulus like we can find many of them in Greece, for instance. And here, of course, you have to deal with the horizontal or nearly horizontal muons, and the job is a little bit more difficult than in the large pyramid when where you can have muons coming from wherever you want. And in the geoscience, of course, there is a lot of use in the volcanology, but also in the characterization of geological layers, in hydrogeology, and so on and so forth. And we will see also that this is interesting in the atmosphere physics. So basically, the two constraints that you have to keep in mind when you make muography is one, statistics, and two, statistics. Okay, so you have to fight with the statistics. This is really what will limit and what will make the constraints of your experiments. The second constraint is also that muons are coming from above. And so you're sensitive only to the above the horizon of your detector. So if you want to characterize, for instance, what is going in the subsurface or in the underground layers, you have to be below whatever you make. So the first case is on the left here, you put the detector here on the slope of a dome, and then you detect the muon which are crossing your dome, and this is the business. And you have to fight a little bit with some backscattering particles that mimic also particles coming from the dome, and which makes you a lot of noise. And this is a difficult part. If you can combine these muography measurements with a more, let's say, traditional measurement for geophysicists like gravimetry, this is something that we have done. And this is something that is really improving a lot the resolution, since you combine, of course, the kernels of the gravimetry and of the muons, which are different and complementary. If you want to go from the radiography to the scanner, to the 3D imaging, you do as the physicians do. You put some more detectors all around the domes, and at least three. Okay, 3D means at least 3 points of view, which are crossing their line of sights to get some common volumes here. Because of course, when you detect an attenuation of the muon, you cannot say that there is an anomaly in the density here or here. This is getting exactly the same results for you. So unless you go around your targets and you confirm the hypothesis of the presence of the density at a certain point of the trajectory, you cannot make an absolute prediction of where the density is. If you go underground, so you can try to localize where are the faults or the cavities or whatever. Of course, you can apply all of these techniques in the industrial controls. You can do some nice application in the tunnel boring machine, and if you're lucky and if you develop a detector which fits inside a borehole, of course, you can also play a little bit with the prospection and mining fields. So inverse problem, the difficult part of the job. Schematically, what you use are either crossing muons in blue or stopping muon in red. So the two are used in the absorption muography, so-called absorption muography. Or you could also use the muons in green, which are crossing the matter, but with deviation. So the last point requires that you measure the track before and after the target. So this deviation or scattering muography here that you see here is applied for, let's say, smaller targets, smaller structure, of course, because you cannot do this for the dome of a volcano, because the size of the detector that you have to put at the entrance would be too large. So basically what we use is either the loss of energy when crossing the matter of the particles. Here you see a quarter of the CMS experiment at CERN, or the scattering, the Coulomb scattering of the particle, and both phenomena are sensitive to the density of the matter which is crossed. Okay, so basically the observable that we're sensitive to is the density through one or the other phenomenon here. And as in the medical imaging, of course, images are absolutely impossible without the reconstruction, meaning the inverse problem solution, because otherwise we just have raw data, and raw data, you cannot do anything with this. So I always show this small picture here to give you the set and the range of either resolution in time or in space that you can get with the muography. Here you see that you can solve really fine structures for small objects using scattering tomography, where here the resolution that you get is roughly millimetric size. Okay? Here, in the case of a volcano, you have, of course, a resolution in the voxels that are typically 10 meters times 10 meters times 10 meters. But this is the reconstruction of a very large structure. Okay? So this is the extreme resolution that you can get. To do an image like this, you need a couple of months of data taking, while to do an image like this, it's of the order of the hour. So when the people always ask, because this is always a question that we get, what is the resolution that you get in space and time with this technique and so on and so forth? The answer is it depends. Of course, it depends of the size of the anomaly that you are looking at in the size of the target that you have. And this fixes some numbers for the application that we get. So as I told you, of course, muons are produced in the atmosphere, so they are sensitive to the parameters of the atmosphere. The first of them being the atmospheric pressure. The higher the pressure, the less muons we get on the ground, because of course muons are absorbed in the atmosphere, so the matter that they have to cross is denser when the atmospheric pressure is higher. And not only this, but also the pions that give birth to the muons, they also have to, let's say, decay to give birth to the muons. So they have to be to propagate in the atmosphere without re-interacting with the atmosphere particles, because otherwise they do not decay and you don't have the muons. So this is not only something that is decreasing the muons because it absorbs them, but this is also playing on the flux because the parents of the muons are affected by those change in the atmosphere. And this phenomena depends on the energy, because of course, the higher the energy of the pion, the longer it will propagate in the atmosphere. So the higher the probability of reinteraction will be also as well. So this is something that is a little bit more tricky than what we could first think. But basically here we made a small experiment on the water tank. Of course, we put the detector, and here we recorded in black the raw data flux, the raw muon flux, and we put it in correlation with the blue, the water level that is measured by a gauge inside the water tank, and in green by the atmospheric pressure. So you see the good anti-correlation that you get with the atmospheric pressure with those two peaks here that are quite clear in the global phenomenon that affected the raw data, the raw muon flux. And of course, you see the perfect anti-correlation between the water level in the tank here and the muon that are measured in the detector. So this is something that we observed, and that may be very interesting. We had at a certain point in 2017 a detector in an underground lab, which is in Switzerland. This was for a completely different study. And we observed that there was a very sharp increase at the time scale of 1 month. So 2 weeks increase, 2 weeks decrease of the muon flux. And this increase was perfectly coincident with a phenomena which is called the sudden stratospheric warming, where the polar vortex turn around here. So the star is the location of our detector. And you see that there was a huge increase of the temperature locally here at the top of our experiments for, let's say, 2 weeks. And then 2 weeks after, it came back to normal. So increase of temperature means decrease of the density of the atmosphere means increase of the muon flux. And so we can follow here some really interesting phenomena occurring in the top layer of the atmosphere. And this was quite a nice measurement with a detector with the 1 square meter of surface that you can build with your students if you want. So this is another appealing, let's say, part of the muography. So focusing now on volcanoes, we collected data on the 4 different volcanoes. One is, of course, the Soufrière of the Guadeloupe. Now we install an experiment on Icelandic volcano in June of this year. We went on a big volcano in the Philippines, which is called the Mayan. And we started really an experiment on the Etna 10 years ago. And this is the installation that we made on the South Crater. Now those place doesn't exist anymore. Of course, it has been destroyed by an eruption of the Etna. And if we have left the detector at that place, it would have been completely destroyed. But of course, life is life. So this is the puzzle game we play to mount a detector on the field, of course. So we mount it field piece by piece. And this is why also you have to design a detector which is quite modular, that you can handle by hand, because here you're just in the middle, in the pampa, in the middle of nowhere. And so you made the first calibration run, and then you put it in the tomographic mode, and you look at the target that you have just in front of you. This is the Snaefell circle. So the Snaefell circle, for the short history, is the point of entrance to the journey to the center of the Earth of Jules Verne. This is also why we put it there, because there is a strong link between the French and Icelandic parts in this on this volcano. And coming back to our beloved Soufrière, we installed at around the dome 6 muographic stations, which made, let's say, one of the world's largest muon station observatory in the world. So you see that our detector was lifted from time to time thanks to the helicopter of the, let's say, civil guard. And with this, we made quite nice tomographic views of the volcano from a different point of view, where each time we managed to see that the structure is not homogeneous at all. There is not a central conduit that, as one could imagine, but this is really a volcano which is made out of subsurface cavities. And of course, with all the rain activity falling on it all the years, this the hydrothermal system is really active and is really large, really big. So actually, we performed another nice measurements by combining gravity data and muon data. So here on the left, you see all the measurement points of the gravimetry. And on the right, you see the 3 detectors that we used for the analysis. And the reason why we made this trial is, of course, that gravity and muons are sensitive to the same observable, which is the density. Okay, so you can jointly invert the data, and this is the easiest way to do it. And so this is something that we developed in an underground lab, which is called the Monterey lab in the Switzerland. So we made measurements with the muon detector being around the dotted red line here, and we made the measurements for the gravimetry on the top of the mountain. And here is basically the results that you get by trying to solve the different densities here of the different layers that we get in the marl, clay, and the limestone, which are basically known. This is a development lab. So for the muons, of course, you can constrain the data above the horizon, and you see that below the horizon of the detector, basically what you say is nonsense. For the gravimetry is the contrary. You have a kind of sensitivity which go quite deep, but of course you have a lack of resolution on the top of the reconstruction zone. And when you join both data, you see how nicely you resolve here your zones, which is here summarized on this graph, where we see the different density which are well separated from one from another, and all over the zones. So combining gravimetry measurements, which are surface measurements, with the muon measurements, which are side measurements, you can constrain the resolution also in the depths, which is not something that you could let's say imagine before, but this is something that is working quite well. And by doing so, we could made the 3D reconstruction of the volcano itself. And here is a comparison between electrical tomography measurements and the muon plus gravimetry measurements. And you see all those common zones here, which corresponds to negative density anomalies that we can recover all over the stuff. So there is a very nice correlation between both reconstruction techniques, which made us very confident on the power of the muography reconstruction stuff. As I told you, the time evolution and the monitoring capacity of the technique is perhaps the most interesting stuff that we get. And here is once more a correlation that was made between seismic analysis with the geophones, which were placed here on the summit. And there was a noise, an increase of noise that occurred in this analysis, and then the wavelength analysis, analysis, identify a location here, which is this yellow volume, where the increase of noise were coming from. And looking at the data on the muons and splitting the acceptance window of the detector that was placed below the zone by chance, we see that here there was a sharp increase in one of the direction of the detector, while the others were keeping slow and were keeping quiet. So we had a huge correlation of here an increase of the muon flux, which means that there was a volume that was getting empty and that was evacuating fluids somehow, generating the noise that was detected on the geophones and making this huge increase of the muon flux with respect to the other zone that we use for controls. So of course, our geophysicist colleagues, they are really fan of the method because they want to use this evolution equations of the hydrothermal system in order to put constraints on the model of the simulation for the heat transfer from the magma chamber to the surface of the volcano, of course. And this is one of example of the simulation that they try to make. And this is, as you probably know, not an easy business. So what I wanted to show you here is that with respect to geophysics and in particular volcanophysics, we enter a new area of multi-messenger geophysics, where not only we can constrain the system, complex system such as the volcanic dome with the traditional methods like electrical tomography, gravimetry, seismology, whatever, but we can also make profits from the geoparticles that we are detecting. The first of them being the muons, but then after we will hear from neutrinos. And so we can get information with the different features that may complement of course, the whole imaging that we can make of volcanoes such as the Soufrière over here. So my conclusion on this would just be a repetition of what I said. So as I told you, muography nowadays is applied in the geotechnical field, and we made many proof of concept measurements on the nuclear power plants, on the tunnel boring machines, on the blast furnace, on the containers of different kinds, okay? And industrial are really pushing in order that we, let's say, produce certified measurements and certified images that they could use in their non-destructive testing of their apparatus. Of course, there have been a lot also in the ancient times, let's say, a lot of trials of applying this muography measurements to the archaeological targets, such as pyramids, tumuli, whatever. And one of the natural use of the muography is also to characterize the geological layers as soon as you have an underground lab and not needed to go as deep as the Gran Sasso lab, but you can make profits of let's say any highway tunnel that you get, and you characterize quite easily the geological layers that are just above your head. Okay. Last but not least, and this will be my concluding slide, this is a technique that is now so popular that even the New York Times made an article on it, and you can find this on the web. Okay, how do you see inside a volcano try a storm of cosmic particles? So this is just to set the scale of how popular this field is becoming nowadays. I thank you for your attention.
Thank you, Jaques. Very, very interesting. There are questions with former director of Gran Sasso.
You stated that both energy loss and scattering provide information on matter density. Actually, the energy loss depends on the average electron density, while scattering depends on the average density of the square of the nuclear charge, or to say it better, on the radiation length. So measuring both, you should be more ambitious, because measuring both, in principle, you get information on matter density, but also on matter composition.
Yeah, and of course, we are also, everything is measured, is multiplied by the Z/A ratio, which is also sensitive to the chemical composition of what is crossed. Of course, in case we can combine both, we do it. But for this, to do the scattering density, you have to measure the trajectory before your target. And if you want to do this on a relevant volume, of course, in the case of a volcanic dome, then I cannot imagine the size of the detector that you have to invent for the Vesuvio, for example. Yeah, you have to surround. One thing which is hidden here is that in the case of scattering, you also need information on the particle momentum, because this is in the formula of the scattering. And this is something that is often left aside by the people who are claiming that they are doing scattering measurements. And measuring the particle or momentum of the particle on the field detector, which is a small size, etc., is not an easy business. Of course, so you have to be quite smart in order to make an inference, reasonable inference of the muon momentum that you are using to reconstruct your business. So of course, I fully agree on this. You can be more precise, but then it's a matter of order of magnitudes also. When you know that the incoming flux, you don't know it better than a few percents, for example, and I think that this is one of the reasons why we want to measure this more precisely, then every detail in the formula is completely washed out by the errors that you get on the simulation itself. When you make the tomography of volume like the Soufrière, you have 5 orders of magnitudes of decrease in the flux. So this means that you have to know and to believe in your model quite deeply, and to have a good accuracy on this.
Thank you. Other questions?
Some about the joint inversion, muon and gravity. Which kind of algorithm we use it, and the modeling we use it
2D, 3D, or to reduce the yield pose a problem?
So, so this is not my my complete specialty here, but what we do on the muographic side is that we use a Bayesian approach. Yes, we make a Bayesian model with as much a priori information as possible. One of them, of course, being the external topography of the target. This is the, let's say, the minimal that you have to put inside your model. Concerning the gravimetry, then of course they remove all the Bouguer anomalies and so on and so forth. And then for the Soufrière, so the Soufrière is quite a complicated stuff in itself, because there is also all the tides effects. Since you are close to the ocean, so there are the ocean tides effect and the earth tides effects that you have to remove. But this is something that is quite under control, in the sense that these are now decades that they are making gravimetry measurements, and they have let's say 1, 2, 3, 4. They have 5 reference points all around the domes that makes possible to have let's say relative measurements to cover the full dome of the Soufrière with the gravimeter.
Other questions?
I have a question. At a certain point, you mentioned faults, and the question is, what are you sensitive to? Like different densities of different rocks displaced by fault?
Yes, exactly. Vacuum is the most is the easiest part that you can detect, of course, because this makes you the large increase in the muon flux. Okay, you don't have any matter, don't have any interaction. Yeah. So force you see perfectly in the stuff.
Other questions? Curiosity for the inverse problem. I assume that the processing of images is quite an important part of the job. I'm wondering if the modern techniques that now are being more and more used, like neural network, machine learning, is helping in improving the quality of the reconstruction, the quality of the resolution of the images.
So actually, to me, the theory of the inverse problem is already some machine learning technique in itself. And so we made a trial to improve, let's say, the resolution and the reconstruction, but not in the inverse problem, in the direct problem. How we remove false tracks from a real signal and so on and so forth. And this is where the neural network is really powerful. So you train this on the Monte Carlo simulation. You train this on distinguishing electrons from muons, scattering particles from crossing particle and so on and so forth. And by improving the signal of a noise ratio in the direct problem, then you improve the reconstruction. But actually, we didn't try yet, and this is something that we are doing for the scattering muon tomography, for instance. Because the scattering stuff, when you have the muon crossing, of course, you have to imagine where the muon made the scattering. And of course, it didn't make one single point of scattering, but most probably he made a lot of scatterings inside of the stuff. So actually, where machine learning can improve your stuff in the scattering is twofold. First, you can train neural network on the path, different path that you simulate directly for the scattering. And the second idea is what I said before, is that you need some knowledge on the momentum of the particle. And so you can here train also with the machine learning, the algorithm to do without real information on the momentum of the particle. So those techniques, they're really useful, but at least we didn't try in the inverse problem, but we try to improve the direct problem.
So if there are no other questions, let's thank Jacques again.
Thank you.
And we move to the next speaker, which is Nicola Rossi from Ivan Sasso Laboratory, and they will talk about the precision measurements of the Earth orbit with solar neutrinos.
Okay, good morning. Thank you, of course, organizers, for the invitation. I will tell another story about the Earth that is different from what we heard this morning, but we will consider the Earth as a planet that is rotating around the sun, of course, and is collecting neutrinos from the sun. And this kind of detection that was performed by, of course, by the Borexino detector that we will see in the afternoon is important also for the geo-neutrino physics, and there will be a presentation from Livia. We will see that Borexino made it possible, thanks to its stability, the detection of the Earth orbit parameters using only neutrinos. Of course, we all know that the Earth orbit is an ellipse. How should I change this? Pointing? No? Okay. So we all know that the Earth orbit is an ellipse, of course, but it's interesting that we do this using another signal, that it's not the optical astronomy, let's say. But we do this thanks to the solar neutrino physics and to the particle physics. The result that I will present appeared this year in this paper, and this paper is important for two main reasons, at least we think about this in this way. First is a philosophical reason. We will see that how important was understanding the relative position of the Earth and the Sun in the history. It was also important for the growth of the science and the rediscovery of the science in the Renaissance, thanks to Galileo and the others. And then it's important also for our for the detection of solar neutrino physics, because we can prove in a different way the high precision achieved by the Borexino detector in the stability of the energy and the response of the detector over more than 10 years. Just let's say a few words about the philosophical importance of this work. We know that there was this debate about what is the relative position of the Earth and the Sun in the universe, very well summarized by the famous dialogue by Galileo Galilei. But it's really interesting that the first heliocentric hypothesis was done 300 years before Christ by this guy that is Aristarchus of Samo, who made also important measurements, because he first determined, for example, the size of the sun, the distance between the Earth and the Sun, the distance between the Earth and the Moon, and the size of all the objects of interest in our solar system. And this guy simply understood that if we place the sun in the center of the universe, you can simplify all the apparent motion of the planet. You can avoid this strange motion back and forth of the planets as the retrogradation motion of the planet. And then, surprisingly, let's say 405 years later, Claudius Ptolemy inverted again the problem and replaced the Earth in the center of the galaxy, but it made more complex all the mathematics, because in order to understand the motion of the planet, he introduced the epicycles. He made a kind of, we say the Fourier transform of the motion, because the relative motion of the stars is not sinusoidal anymore. You need to add additional correction, epicycles, and epicycles on epicycles in order to explain the fine motion of all the planets around the sun. This debate, of course, came again into the reality in the Renaissance thanks to Copernicus, and then Galileo, Kepler, and so on, and then inspired also Isaac Newton for understanding one of the most important law of the mechanics, that it is actually one of the most important discovery in the history of the physics. But actually, we know that none of the two are correct, right? Because the sun is not rotating, the sun and the earth are rotating around a common barycenter that is very close to the sun. So it makes the Copernican picture of the universe more precise in this sense. But we know that the sun is rotating in the galaxy. So actually, the motion of the earth is not an ellipse, but is an open helix that is trying to following the sun at the speed of 240 kilometers per second and around the center of the galaxy, and the galaxy moves in turns towards the Andromeda galaxy with higher spin, and all the universe is expanding. So the picture at the end is much more complex. What are solar neutrinos and why are important for this kind of measurement? Solar neutrinos are byproduct of, maybe I should use this. It's nice. Okay, are byproduct of the nuclear fusion in the sun. 4 atoms of hydrogen are converted into helium with the production of 2 neutrinos and energy. We know that in the sun, this fusion can happen through 2 mechanisms. 99% of the energy production in the sun is done through the direct fusion of the atoms that is called the PP chain. But 1% is done by the CNO cycle. CNO cycle does exactly the same as the PP chain, but using the carbon-12 as a catalyst. So basically, in the end, we always have a helium atom plus neutrinos. And why neutrinos? Because, of course, you have 4 protons. You have, in the end, a helium atom that is made of proton and neutron. So you need a weak interaction involving neutrinos, able to convert the proton into neutrons. It's really interesting because we know that from the astrophysics that the CNO mechanism is the main mechanism of the energy production in stars heavier than the sun. Okay, because the efficiency depends on the mass that in turn depends on the temperature of the core in which those reaction happens. So for heavier stars, this is the main mechanism. And we are very lucky that in the sun, it's big enough to allow at least at the level of 1% this reaction. And Borexino was able basically to detect all those neutrinos, both from the PP chain, and in the end, we published in 2020 the first evidence also of this very small flux of neutrinos produced in the sun. Okay, and here the ellipse nature of the Earth orbit played an important role because we know that the Earth-Sun distance is not constant because we are moving around an ellipse, that it's very similar to a circle because the eccentricity, it's really small. It's like 1.7%. But this is important because when we measure the flux of the neutrinos, and so we rescale the flux produced in the center of the sun by the inverse of the sphere surface, at the leading order, we have this sinusoidal component due to the shape of the Earth orbit. And the amplitude of this modulation is 2 times at the leading order, the eccentricity. So we have a modulation of 3.4% of the flux in amplitude. It means 7% from the minimum and the maximum, while the Earth is moving around the sun. Borexino has a very long story. The first idea about the detector started in 1990, thanks to Gianpaolo Bellini and the others that started thinking about how to build a detector capable of detecting low energy neutrinos in the sub-MeV region. And so there were a lot of prototype and tests before the real experiment, and the real experiment started taking data in 2017. And now the detector is under the commissioning because it was stopped at the end of the last year. What is the idea of the detector? We know that the flux of the neutrinos coming from the sun, it's really big, no? Because it's 60 billions of neutrino per centimeter square per second, but the cross-section is extremely small. So if you don't put a very huge target, multi-ton target detector, you are not able to prove that all the neutrino, about all the neutrino that we are speaking about. And so the solution is to build a big detector with very clean material, because the energy deposited in this interaction is extremely small. And this solution was done using liquid scintillator, because liquid scintillator can be purified at very record level in order to enable this kind of measurement. This was the real success of Borexino. Borexino is located in the Old Sea of the Gran Sasso National Laboratory, in which the muon flux, just to continue with the presentation, is reduced by a factor 1 million, and the shield of the rock corresponds to about 4 kilometers water equivalent. These are pictures of the detector. This was before the filling. This is the picture as it appears after the thermal insolation that was crucial for the detection of the CNO. And this is a picture taken from the camera of the interior part and inside the detector. Borexino is a big sphere of about 13.7 meter diameter, and is filled with more than 1,000 cubic meter of pseudocumene, and it's made of concentric shells with increasing radio purity. And the real detector, the real target, it's only this 300-ton balloon, in which we reach the best level for the purity of the detector, and so we are able to detect the solar neutrino. The detection principle is the scattering of the electrons of the target due to the interaction of neutrinos. Borexino is using a scintillator, so an ionizing particle is producing light. Light is collected by 2,000 photomultipliers with an optical coverage of about 35% that are placed all around the surface of the sphere. And Borexino and the big sphere is immersed in a water tank Cherenkov detector that is used for vetoing basically the cosmogenic induced background. I was saying before that the real, the real success of Borexino, it was given to the purification procedure, but not only purification, also the selection of the material with very low radioactivity. And the purification was done using different techniques, but what was really crucial in the full process was the water extraction campaign that lasted about 1 year, in which the scintillator is passed through high purity water that keeps all the ionic contaminants in the detector, making the detector reach this very impressive level of contamination, for example, of uranium, thorium, and other contaminant, and especially we will see the background that are basically in competition, that are basically covering the signal induced by the solar neutrinos. Thanks to a very intense calibration campaign performed at the beginning of the detector, data taking, Borexino is able to reconstruct event by event in real time the position of the event with an uncertainty of 10 centimeter and the energy resolution of 5% at 1 MeV. This is the, I just explained the energy spectrum Borexino because we will be used later. The black curve are all events when we do not apply any cut, and the red curve is the most crucial cut. This cut is basically the restriction of the events only to a very small volume inside the inner balloon. That is of about 70 cubic meter, order of 70, 80 cubic meter. Sorry, tons. Very close each other, of course. And only when we restrict the events in the very innermost region of the detector, we are able to see this famous Borexino spectrum. And this shoulder here is the beryllium-7 induced electron scattering. And that is visible, how to say, by eye in the energy spectrum. Then we apply also another stringent cut, that is the so-called threefold coincidence, that is a space-time veto around the muon passing through the detector, that enable us to reduce the contamination of the carbon-11, and we get the highest sensitivity for the detection of the solar neutrino. This is our understanding of the background. The red curves are the signal, the energy distribution of the event produced by the neutrino interaction, solar neutrino interaction. All the rest with different colors are the background. Okay, so our analysis is strictly related to the knowledge, very accurate knowledge of the background contamination. Borexino data taking that goes from 2007 to the end 2021 is split usually in 3 phases that are the green parts. Between the phase 1 and phase 2, we have the calibration and the water extraction that I mentioned before. And then during the phase 2, we realized that the detection of the CNO was actually possible, and we improved the detector, stabilizing the temperature, so stopping the convective motions inside the detector in order to improve the background condition for the detection of the CNO. And so we decided to split this second period in 2 phases, and the last phase is the phase in which we got the first detection of the CNO neutrinos. The analysis I will show today about the seasonal modulation of the solar flux includes the combination of the phase 2 and phase 3. Okay, so it's a period of about 10 years, because we are not using the first part because the background condition is completely different. It's a kind of different experiment. So we decided to keep only the second part, in which the level of the contamination is extremely good. So what is the, okay, just to, okay. You told that we should not show tables. It's true, but this is just summarizing the precise measurement performed by Borexino about the solar neutrino flux from the PP chain and from the CNO, updated lastly in the 2022. Borexino made a lot of important first direct detection of all the single components of the PP chain, and then later from the PP, with a lot of implication that I will not speak about this, concerning the solar neutrino oscillation and the importance of the solar modeling. What is the idea of the time variation? So we need to produce a time series, basically, and then we need to do a kind of Fourier transform. This is the basic idea. How to produce the time series? Time series with just simple idea. We take a region, a fixed window region in energy, and we just count the event rate in this window. But this window is chosen a priori, maximizing a figure of merit. So basically, we selected a region in which the signal to noise ratio is maximal. So the contribution of the solar neutrino in this region is maximal compared with the remaining background. Okay, and this region is found to be in between 300 and 800 something kV. And we also enlarged the fiducial volume. So we took a slightly higher, bigger fiducial volume, because we are caring only about the modulation of the background. So if there is a compromise, because if we increase the fiducial volume, you can get more events also from the signal. Okay, so we realized that the best choice was a larger volume, as compared with the other volumes that we use, for example, for the solar neutrino analysis. And this is the time series of the total rate in the window. Okay? Then I will explain you why there is this kind of trend. Then we apply a simple model of the background that is a combination of 2 exponential. I know that this can introduce a bias, because, you know, if the model is not correct, you can detrend the data and get a signal that is affected by some kind of bias. But we tried also with other models like polynomial modeling or local regression modeling, everything, and we demonstrated that the bias induced by the use of the exponential is basically negligible. So the systematics of the trending with double exponential is extremely good in this sense. When we remove the the low frequency trend, so this green line, we get the residuals. And here there is a sinusoidal fit in which we can see visibly by eye the modulation of the solar neutrino with a period of 1 year. What is the long-term trend? What is the origin? We have many sources of possible long-term secular variation of the background. For example, we have the deformation of the nylon vessel. So since we are taking a bigger volume, the nylon vessel is deformating, is moving with the air, and so external background can come inside and can produce a variation of the background. Then we have long-lived decay as the krypton and the bismuth with a time half-life of about 10-20 years, and this is also can affect the long-term modulation. And then we have the polonium. The polonium, it's the most dangerous in this sense because the polonium is diffused from the inner nylon balloon, and there are convective motion inside that is moving this polonium from the outer part into the center, and this could induce fake seasonal modulation related to the temperature change of the experimental room. But we are lucky because the scintillator of Borexino, it's capable through the pulse shape discrimination to disentangle the alpha particle produced by the polonium decay. So we apply basically the alpha beta discrimination, we remove this component, and the residual of this polonium due to the inefficiency is extremely small, and it's absolutely not affecting our final result. Then what we do is basically a generalization of the Fourier transform that is called the generalized Lomb-Skergol analysis. That is basically a likelihood ratio in which we can treat properly the low statistics, in which we have a we enter in a Poissonian regime because our bin is so small that the counts that enters in the window are small numbers. And so the Gaussian approximation is not valid anymore. This is the power spectrum that is provided by this method. It is analogous to the, it's similar to the one produced by the Fourier transform. They are related to each other. And we see that there is a prominent peak around 1 year, as we already seen from the trend of the residuals in the previous picture, with a significance of 3.5 sigma. Then we do a simple analysis. We perform a sinusoidal fit in which we leave 3 parameters: the amplitude, the frequency, and the phase. And these are the parameters that we get. This is the amplitude that is directly related, we will see, to the eccentricity. Then we have the period that is basically 1 year, very small in days, and a phase. Okay, there is a typo. This is the opposite. I mistake this formula. It's 30 plus minus 20. So we measure the phase, so the perihelion position of the Earth, with an error of about 3 weeks. Then let's go to the eccentricity, that is the most important in this philosophical picture. The eccentricity provided by this measurement, it's the number reported here that is very close to the astronomical number. And here there is a comparison of the Borexino precise measurement done with solar neutrino only, with other solar neutrino that in the past tried to do the same analysis, but they were not giving a significance more than 2 sigma because of a lower rate. So, and the black line is the astronomical measurement, of course, of the Earth orbit eccentricity, and this is the value of the eccentricity, for example, reported in the Principia Mathematica by Isaac Newton. So this is our final result. So 3.68, very close to expected 3.4. With 5%, 20% uncertainty. It's also important because we can reverse the problem. Assume that the astronomy is correct. We know perfectly that the orbit is an ellipse. What we can do in principle, we can measure the variation of the flux in the beryllium 7 window, And we can measure actually the flux of the beryllium-7 using the modulation only. And we get a number that is compatible with our precise measurement and also with the prediction of the solar standard models. So it means that Borexino could have measured the beryllium-7 thanks to the modulation, even if the shoulder, the famous shoulder that I showed before, was not visible by eye. Okay. Then we expanded the periodogram, scanning all the frequencies between 1 cycle year to 1 cycle day, also to study all possible modulation of the neutrino flux, for example, due to the interaction with the Earth. So it's a night and day effect, and so on. So for doing this, in order to match the Nyquist condition for the frequency detection, we binned the data every 8 hours. Of course, now it's not really easy to see by eye the annual modulation, because in the previously we were binning in 30 days, so it was much more visible in this sense. And we performed the full periodogram analysis using the generalized Lomskergol, and this is the final result. Of course, here compressed very close to the y-axis, there is 1 year frequency with the same significance as shown before. And then all the other frequencies are not relevant, since we a priori, we do not know the origin of the modulation of the sun. We can imagine whatever. For example, Vissani was proposing 1 week modulation. Why? Because there is human activity, no? For example, the change of the shifter crew, whatever, can produce some bias in the collection of the data, whatever. And actually, we don't see anything that is relevant. For example, another frequency could be the sun rotation. No, we know that the sun is spinning with a period of 27 days. And also in this case, you can imagine that the production of the neutrino is not symmetric with respect to the center. You can get whatever modulation due to the spin of the sun. Also for the day-night effect that was already published in phase 1 by Borexino, we get a similar result. It's compatible with zero with this uncertainty. So basically, the conclusion is that we have presented the most precise measurement of the Earth orbit parameter done with solar neutrino only. So with a signal that is different from the optical astronomy, completely independent. We have proven the absence of any significant modulations in the full periodogram that goes from 1 cycle year to 1 cycle day. But what is really important is that besides the fact that the orbit is an eccentricity, we know it from neutrinos, it's important because we proved in a different way the very high stability of the Borexino detector in terms of response, energy response, and energy resolution. And we also proved a clear understanding of the background, or all the component of the background present in our detector. Thank you very much.
Thank you, Nicola. There is one question.
I want to ask the motivation of these studies. The motivation of these studies to test the astronomical observations, or to test to constrain the solar neutrino flux using modulation profiles. Which is your motivation?
No. The modulation is not assuming the eccentricity. Is reconstructing. Is reconstructed assuming fitting the data, because the amplitude of the modulation is directly related to the eccentricity. So measuring the amplitude, you get the eccentricity independently of the astronomy.
I understand it. And so you showed the your observation uncertainty is very smaller than the I-scale data. So the to constrain the uncertainty is your motivation, or your final scientific goal is to measure solar neutrinos with more precisely using modulation data.
But you mean in the beryllium-7 case?
Yes.
Yes, in this case, you get you assume in this case, you assume, what you should assume is also the total rate of the sun. For this, you can assume the prediction of the solar standard model. Okay. Okay. So you assume this total rate, of course, and comparing the modulation with respect to the prediction, you get the flux of the beryllium.
I see. Thank you.
Okay.
Thank you. Other question? Francesco?
If I remember well, your measurement of beryllium, I mean, not the one that you reported, the one from constant is more precise than the theoretical determination of, say, standard solar model.
Yes.
And yeah, so in this sense, I think that, I mean, you can rely on your own data, but just my view. I mean, if you rely on this, say, constant, then you can deduce and make.
Yes, but we decided not to do this,
Okay.
even if, because, okay, you cannot gain really much. But in order to make this analysis independent from our previous measurement, that's the reason why we are assuming. Of course, combining all the possible models, you get a very large uncertainty.
Absolutely.
Of course, you can reduce.
Yeah. Then something which is sort of psychological. I felt some, say, surprise of people around who are not in Borexino collaboration because of the detector has been, say, closed. I mean, we know the story, but I think that you could usefully comment, or maybe Gioacchino, because I really saw it looking people around.
Okay. In this case, for political reasons,
The right comment should have been done by the director, which unfortunately
disappeared.
Had to left, maybe because he knew your question in advance. In any case, the issue is that now the detector, has been shut down on 1 year ago, October of 2021, and probably we could have get other 2 years of good data, because the lifetime of a detector was not yet over. But okay, motivation which are not above science dictated this decision from the INFN match. Other questions? Marco?
What do we actually mean by the astronomical? I don't know if you know the astronomical eccentricity. Like the sun is not. Is it included all the? It's very precise, of course. But I was wondering if we know, if somebody know, if you know, if it includes the fact that the sun is not infinitely massive. To what extent the astronomical knowledge of the orbit is actually takes into account effects like
yes, it's quite
solar
complex.
oblateness, these things.
Exactly. I tried. There is a very nice page in the NASA website in which this is reported. No, it's a very complex result that includes all possible deformation. But we know also that the eccentricity is it's not fixed in time. It depends on the Milankovitch cycles. No, because there are periodic variation of the different, for example, the orbit that is kind of squeezing back and forth, and it takes like centuries for making this kind of movement. So they include all possible variation, and they have also a modeling for those possible Milankovitch cycles. So it's extremely accurate.
Other questions? Can you remind us, this is a normal question when there is a modulation measurement at Gran Sasso. Can you remind us of the phase of the Dama modulation?
No, the phase it's 1 month before, because the dark matter phase is June 2nd.
So there is just 1 month of difference.
Yes, while the modulation induced by the how to say, the perihelion motion is at the beginning of July. As the muon, no, because also muon flux is modulated, that it's coincident with this measurement. So cannot explain the Dama signal, no.
Okay, just to do a standard question.
Okay.
Other issues or questions? No, so we are 5 minutes ahead of schedule. So thank you, Nicola, again.
You're welcome.
Okay, so I think that now the lunch is in 5 minutes from now in the other room. Giusto? They are just ready. Okay. When they are ready, we can start. If there is already a lunch, we can start immediately. And we reconvene according to the schedule. With the third session, we reconvene at 10 past 2. 10 minutes past 2. So.
That we can resume the sessions. Okay. So we had some change in the agenda because Fabio Mantovani cannot unfortunately be here. And so the first speaker is going to be Nanami Kawada, and we will speak about the geo-neutrinos detected by Kamlan. So, okay, you can take it on. It's better if you speak inside. Okay. Yes, I think, okay. Okay, fine, please start.
Okay, I talk about spectroscopic measurement of geo-neutrinos from uranium and thorium with Kamlan. This is the latest result from Kamlan. So this study approaches properties inside the Earth. So firstly, I'd like to show review traditional geoscientific approaches. As you know, seismology reveals structural modeling by earthquake analysis, and they reveal multi-layer structure in our planet. And as for chemical properties, geochemistry and cosmochemistry gives computational estimation based on rock samples and chondrite meteorites. And as for heat study, geoscience gives heat flux measurement at the surface and so on. And there are many other approaches. However, there are some open questions like which type of meteorites form the Earth, and what powers the geodynamics, and how much layers the matter have. And we think the geo-neutrino is a key of this question. So we are doing neutrino geoscience. In this study, we especially focus on geothermal evolution and geodynamics. You know, the history of the Earth is basically a global cooling process from magma ocean, and the geodynamics are powered by heat inside the Earth. So understanding the heat amount and its source is very important to study our planet. Surface heat flux measurement gives the measurement of total heat amount of our planet, and to be around 47 plus minus 2 terawatts. And the source of it is thought to be primordial heat and radiogenic heat. However, the breakdown of these heat sources can never be known by heat measurement. Among these heat sources, we can group think that heat generated by radioactive elements, radiogenic heat is especially important because once we measure the present amount of radiogenic heat, then we can know the amount of radiogenic heat through our planet, because uranium and thorium and such any other heat producing element decays according to a certain lifetime. So this radiogenic heat is especially important for understanding the geothermal evolution of a planet. However, there are some different predictions of the amount of radiogenic heat from geophysics and geochemistry. So we think that direct measurement of radiogenic heat is necessary. And it is the motivation of geo-neutrino observation. In the Earth, there are heat-producing elements such as uranium and thorium in the crust and mantles, and they emit anti-electron neutrinos, a kind of elementary particles, and heat, radiogenic heat here. And once we measure the flux of geo-neutrinos using Cameron detector, Bracco detector, we can convert it to the amount of uranium and thorium. Then we can convert it to the amount of radiogenic heat. So by measuring the total flux of geo-neutrinos, we can test the Earth's heat budget. And in addition, uranium and thorium and potassium has different energy of neutrino emissions. So by measuring a spectrum of geo-neutrinos, we can even test the uranium thorium ratios, then we can test the Earth's chemical composition. This page shows the estimation of geo-neutrino flux models. Basically, generally, geo-neutrino flux is calculated from knowledge of particle physics, such as decay rate of heat-producing elements and their luminosity per decades, and survival probability that one geo-neutrino can propagate to the detector under the oscillation effect. And geoscientific parameters, that is concentration of uranium and thorium in each reservoirs in the Earth and their densities. So in our study, we adopted our reference estimation published by Enomoto et al. 2007. And in these estimations, crust and sedimentary part is calculated based on cosmochemical and geochemical studies, that is rock sampling and meteorite sampling. And any local geological effect is averaged and taken advantage in the calculation of uncertainties. However, the dominant uncertainties in this cluster and sedimentary part came from uranium thorium concentration measurement on the Earth. So we think this is a very robust estimation for cluster and sediment. On the other hand, mantle part is calculated by subtraction of crust plus sedimentary part contribution from BSE compositional modeling. So we'd like to test this with geo-neutrinos, and in other words, mantle part is the region of interest of our study. We use Cameron detector to observe geo-neutrinos. Cameron is located at the almost center of Japan, and it is installed under the mountains. And this is a schematic view of our detectors. And this detector has two layers. The outer layer is 18-meter diameter cylinders, and it is filled with purified waters and mounted at about 200 of photomultipliers. And this outer detector provides passive shielding from outer rock of the detectors. And also it provides active veto to muon. And in this cylinder, another spherical stainless steel tank is installed. And this is the main part of Cameron detectors. There are almost 1 kiloton purified scintillator. This is basically generally a mixture of soil comment and Regan and PPO is installed. And when neutrino comes and react in these reactors, there are scintillation emission, light emission. Then such scintillation light is captured by about 2,000 photomultipliers mounted on the inner surface of this spherical tank. And then from this scintillation photon properties, we can reconstruct the energy and the vertex of scintillations. Then neutrinos, anti-electron neutrinos are detected via inverse beta decay channels, as you know. When anti-electron neutrinos react with proton in the liquid scintillators, they emit positron and neutrons. And positron make annihilation to gammas, so this is one scintillations. And on the other hand, thermal neutron is captured by protons, and there is another gamma ray emissions, and there is another scintillations. So by taking twofold coincidence of these two scintillations, we can make almost background-free very good anti-neutron profiles. This is the primary advantage for Cameron to observe the geo-neutrinos. And another advantage is energy reconstruction. The amount of scintillation photon is almost related to the energy of incident neutrinos, so we can reconstruct the energy of neutrinos from the scintillation event, and that's why we can test the spectrum of neutrinos. However, there is disadvantage that this reaction channel do not provide directional information. So reactor neutrinos, anti-electron neutrinos from reactors are the dominant background. And next page shows the data set of this report based considering the reactor neutrinos. This figure is time versus estimated neutrino flux from reactors. And so total is Bracco. So please look at the Bracco plot. As you can see, reactor neutrino flux is very high in these 10 years. However, it suddenly significantly reduced here. This is correspond to, as you know, the Great East earthquake in Japan. And almost all reactors in Japan have suspended. So reactor neutrinos reduced significantly. So this reactor period gives a very lower reactor neutrino spectrum. In this past 10 years, there is out of reactor spectrum like this, and geo-neutrino spectrum is totally covered. However, in the reactor period, reactor geo-neutrino spectrum appears on the reactor neutrino spectrum. So this reactor period gives us a very large signal to noise ratio of geo-neutrino observation. So basically, our latest result is with precise observation of geo-neutrinos using this reactor period. The number of geo-neutrino signal is determined using the ambient likelihood method using all data provided by Cameron, event rate and event energy spectrum like this, and time profile shown very complicatedly here. This is the best fit background models and signal shape with different colors, with the actually observed spectrum with black point in each time period. Let me show the difference in each period. At first, from period 1 to period 3, this green background was suppressed significantly. This background is alpha background, like this diagram. This is very complicated background, so I don't tell you the detail here. But the point is that this reaction mimic neutrino signals. And also, this reaction is triggered by one alpha particles. So the suppressing alpha activity in the detector is very important to suppress this background. And the main alpha source in Cameron detector is polonium 210, and main polonium provider is lead 210. So to remove these isotopes in the liquid scintillator, we command group performed 2 times distillation campaign of full volume of liquid scintillator in 2007-2008, and as a result, polonium activity was reduced by factors to this level. And as a result of this distillation, alpha background was suppressed significantly, And in this period, it is almost negligible. Then period 2, reactor neutrino is next dominant background. However, as I said, this reactor neutrino is significantly suppressed by the reactor of environment. So in period 3, we can see the apparent geo-neutrino signal shape like this shaded spectrum. And this is thorium contribution, this is uranium contribution. This is another view of the best fit background model. As I said, in period 1, there is a large amount of alpha n contribution, but it is suppressed in distillations, and in period 2, it is almost negligible. Reactor neutrino is still there in period 3, but it is suppressed in period 3. So in period 3, the geo-neutrino spectrum is apparently detected here. Before going to geoscientific discussion, I would like to show the significance of period 3. If I apply the spectrum fitting in only period 1, the determined number of uranium geo-neutrino event and thorium geo-neutrino event is these contours. Best fit and 1 sigma 2 sigma 3 sigma delta chi-square profiles. In period 3, this is this green contour. But in period 3, it turns to this small orange contours. So the narrower the contour is, that means period 3, reactor of period, contributes to the determination of geo-neutrino from uranium and thorium significantly. Then let's go to geophysical, geoscientific discussion. This is our result of geo-neutrino flux from uranium and thorium, and best fit point and 1 to sigma. And then projection to this contour to each axis, we can get one-dimensional confidence intervals summarized like this tables. And as you can see in this column, there was signal rejection. It can be said that commonly detected significant geo-neutrino signal from both uranium and thorium inside the Earth. And in other words, spectroscopic measurement of geo-neutrinos from uranium and thorium was achieved. Then the total measured geo-neutrino signal can be divided into cluster contribution and mantle contribution. The cluster contribution is estimated very precisely using some geochemical studies like this small collapse. So the lighter upside is thought to be mantle contribution. Then the mantle contribution is converted to radiogenic heat, like this equation. The total from the total measured geo-neutrinos subtract cluster estimation. Then this part is flux from uranium, thorium in the mantles. Then times the conversion coefficient between flux and radiogenic heat in homogeneous mantles, we can get the value of radiogenic heat. And this is the contour of radiogenic heat from uranium, thorium in the mantle. And band is correspond to the conversion uncertainties from coming from cluster uncertainties. Then reading the overlap of our common contours and this radiogenic heat contours, we can find that the total measure the value of radiogenic heat from uranium, thorium in the mantles. Then I could put some model estimation from the geoscience on this map. So this green bar, low bar, blue bar is low Q model and middle Q models. These are generally the BSE model based on carbonaceous chondrite and N-satellite chondrite. And as you can see, apparently these two models is very consistent with our latest data. On the other hand, high-Q model, this is a geophysical estimation based on balancing mantle viscosity and heat dispersion, and predicting relatively larger amount of gradient heat to drive the mantle convection. And this is inconsistent with our latest data. To evaluate the tension between this the common result and its models, I projected this to the contour to this axis like this, and this is the projected common the delta chi-square profile, one axis, and one sigma interval is cut here, and corresponding models are written here and here. The high-Q model is apparently has tension between common data. The tension between observation data and the model is basically got by reading the delta chi-square value at the position of models. However, model itself has uncertainties, and also cluster estimation also have uncertainty. So we need to evaluate the tension conservatively, taking consideration of these uncertainties using these very complicated statistical calculation. This is very complicated calculation, so I do not tell the detail today. But the point is that as a result of calculations, this high-Q model is disfavored at 99.76%, assuming homogeneous mantle compositions. And if we assume uranium thorium in the mantle is concentrated at the mantle core boundary, so in such a situation, this red bar slightly shifts to the left, and it is a little harder for Cameron to reject it. But in such extreme assumptions, high-Q model is disfavored at 97.9%. So this high-Q model is completely disfavored by latest common result. Then a high-Q model is originally based on seismology data in my understanding. Then they extracted density and viscosity profiles in the mantles, and then they gave the geodynamical calculation of one layer mantle convection to predict a relatively larger amount of radiation heat around 25 terawatt. So high-Q model rejection in Cameron data indicates that we need to modify the mantle viscosity or density profiles extracted from seismology or in the geodynamical modeling of mantle convection. On the other hand, the Cameron data accept low Q and middle Q models, and these two models are based on geochemistry and cosmos chemistry. So they are the heterology of mantle composition. So that means this result suggests mantle multi-layer convection. Finally, the Cameron experiment has been measuring geo-neutrinos from uranium and thorium for more than 20 years. The reactor of period in Japan suppressed the reactor neutrino background significantly and enables a spectroscopic measurement of geo-neutrinos from uranium and thorium. The Cameron data is consistent with low Q and middle Q models based on chondrite composition analysis, whereas high-Q model is disfavored completely. Finally, I would like to introduce our latest publication. The result I talked today is already have been published in geophysical research letters with this DOI. Unfortunately, our paper was selected as research spotlight by the editors of GRL. And an additional article with plain language is also published in EOS.org. So please take a look if you are interested in. That's all. Thank you.
Well, you're perfect in time, or even in advance. Okay. So questions, Nanami? Gianpaolo?
So I perhaps miss this information. You are continuing to take data now, or you stop?
Yes.
Because now we are working on double beta decay, you know.
In parallel.
Yes, and then we have no troubles to detect the geo-neutrinos. We have some complication.
Of course. So actually, this is my PhD work. So the endpoint of data today is this my yes. It's mine.
There, okay, Livia.
Thank you for the nice talk. So I would have two questions. One regards the differences of the results presented in the latest paper with respect to the one which were presented by Hiroko Watanabe at Neutrino Geoscience in 2019 and at TAUP 2020, or Neutrino, TAUP 2021. Yes. So the number of days is quite different in but the exposure is the same. And the number of candidates is different. So by 20. So can you comment from where these differences come from?
The data set is not identical. The data set is not identical. I have additional data set.
But the exposure in the kilot is the same. So you have changed. I mean, it's a bit strange because the number of days is different, but the exposure is the same.
Exposure is different.
I just checked on the slides. It's 6.3, 10 to the 32. Okay, we can maybe in the slides and in the paper. I found
it should
the
be
same.
different because Hiroko's data is used. She didn't use the data for 2020, but I include them. So exposure should be different.
Okay, maybe I just checked on the slides, and it results to be this. Okay.
Yes,
but
and I have one more comment. If I add 1 year data set, it is only 5% of common full data set, but it is 10% of low reactor of period.
Yes.
So it is more significant than
Yes. Maybe we can check offline together what I have read.
Please.
And then on slide 13, if I would like to ask.
Can you see myself? 13?
13. So the uranium, thorium, yes. So when I look, you are saying that you reject 0 uranium at 3.3 and thorium at 2.4 almost sigma. But I see that the 2 sigma contour is crossing the 0 line of thorium. How is this possible?
It is due to the difference of degree of freedom.
Okay, so it's in the 2D. Okay.
Yes.
Yeah. Okay. Okay.
If you have a question. If you can go back by one slide, okay, the 12. Please, Livia.
Can you see my slide?
Could you put the presentation? Uh, 12, yes. So I noticed that depending on the period, the dot that corresponds to the evaluation of the uranium moves in these directions.
Sorry.
While the thorium is in the number of events of thorium is more or less the same, the number of uranium seems that it moves to the left. So practically you get a smaller amount of, this is due to the statistics.
Sorry, please.
Sorry?
More slow English, please.
Okay. So which is the reasons for while you are getting, because it is normalized to the time, okay?
Normalized, yes.
So, and it seems that there is some systematic effect because the reduction of the background, I believe, cause a reduction of the number of uranium. This is just understand why, okay? Is it less backward? It is just a case.
Because the uncertainty is very different, so.
No, I look just at the central point, this one, the best.
But the tension is only one sigma.
No, yes, sure. But I noticed that there is, while the number of thorium events divided for the time looks consistent for the 3 data set, look, the number of uranium seems that decrease. So, I mean, the period 3 gives a smaller amount. I want just to understand if I understood correctly the plot. It is true.
It's true.
Ah, okay, no, just so I thought that or it is a chance or it is correlated to the fact that some background is mostly mimicking uranium instead of thorium's events, something like that. And so what the background that you reduced caused a decrease of the uranium. This was, let's say, you do not have an answer, I believe, and so, okay, just I noticed this. Okay, so could be related to your background rejection capabilities that has improved, and maybe the background was mimicking uranium in some sense. Of course, the shape is not the same, and so this could be. Okay.
Hi, your convective array ratio is quite low. So now I've even just, so my question is, did you try to calculate the secular cooling? Yeah. Because if you don't have, if you have very low internal heat production, and yet you keep cooling the Earth because there is outgoing flux, then the other part should be picked up by secular cooling. So the question is, how much secular cooling would you predict given your low array ratio?
Sorry, I don't have such numbers.
Okay. Okay.
Thanks. On your last slide, you mentioned about something about changing the mantle viscosity profile.
Yes.
Do you have the slide? I just want, could you just explain why?
The reason of this?
Yeah. Why does the rejecting the high Q model imply a need to modify the mantle viscosity profile?
Because this 25 terawatt prediction is based on this dictionary. So if this is incorrect,
and what mantle viscosity
piece of this needs to be modified.
Okay. And what mantle viscosity profile did you use?
What mantle products?
I mean, there are loads.
So in my understanding, this model is based on seismology, and then they extract the velocity and density profiles, and then they apply geodynamic calculations with one layer assumptions, and they again that prediction of 25 terawatt. It is my understanding, and if it is incorrect, there should be some incorrect points in these strategies. I mean,
yes. Okay. All right.
Maybe we could specify that current seismology takes the Earth as an elastic medium, not so PREM will never give you viscosity, because viscosity is for a viscous reaction, not an elastic behavior. So be careful.
Okay, thank you.
I have a simple question because I'm confused. But if I understand, the reactors now are on in Japan.
Sorry?
If the reactors, the nuclear reactors, now are on in Japan, are not off.
Reactors? Almost all reactors in Japan is suspended, but we take account of reactors all over the world. Not those points.
Okay. Now, excuse me, if I understand now, the reactor are not all switched off.
It's not all switched off, and some
Even
is
now?
restarting now.
Even now,
Yes.
How many are working more or less now, are in function reactors?
Sorry.
How many reactors are working now more or less? Just
I have forgot, but the government of Japan says that Japan will restart almost all of reactors soon. So probably now about 20 or 30% of reactors is in working. Probably.
Okay. Okay. Are there other questions? Okay. If not, okay, we can move to the talk.
Thank you. Yes, let's see. Okay, hello everybody. So thanks a lot for organizing such a nice interdisciplinary workshop, and thanks for the invitation. I am going to present the results about the Borexino experiment, but as I learned this morning, unfortunately Fabio Mantovani could not come, so I made some last moment adjustment in my slides to wrap both the part of the introduction, some outlook and comparison of Borexino and Kamland results. So I will do like both talks. I would like to invite everybody, please don't hesitate. I am not loud enough, wow. Please don't hesitate to interrupt me. I mean, I have also background in metamorphic petrology and also in neutrino physics, but there can be some incomprehensions, difference also regarding Kamland latest results or from geophysics. So we are here to learn. So please interrupt me if I'm saying something which you think is incorrect. So welcome to this journey to the center of the Earth. And as I used to say like the seminar last week, I had that at the end of the seminar, I might ask for the answer, what is wrong in that title, that why we are not speaking about what is in the center of the Earth, but in the interior of the Earth. So I will go through the introduction of geo-neutrinos, what kind of studies we can do with geo-neutrinos, to the geological people coming from the geosciences. I will explain some basic characteristics of neutrinos, and then I will dive into the details about the Borexino results and about the interpretation, comparison with Kamland and outlook of this field. So there are many processes on the surface of the Earth that are demonstrating a lot of energy which is buried and hidden in the deep in the Earth. It can be such a terrible events like is the picture of the photography, unfortunately, of the earthquake which occurred in L'Aquila, so close to the Borexino experiment, which is in such a tragic way demonstrating the power which is inside the Earth. There can be spectacular events like volcanic eruptions, which can be also nice to watch. For example, there is the photo I took in Kamchatka from the Shiveluch volcano, or we can see, like this is a photo from Grand Canyon, how the previous layers of the sedimentary rocks from the ocean floor are brought to the surface of the Earth. And people are asking from where is coming this energy, which is powering all these different processes. And we are trying to discuss here how neutrino physics can help us to understand this question. So what are geo-neutrinos? Geo-neutrinos are neutrinos, practically anti-neutrinos, so antiparticle to neutrinos, which are emitted in the radioactive decay chains of uranium 238, thorium 232, and decays of potassium-40. As you can see, the number of antineutrinos and the energy, so we call it radiogenic heat, which can drive these kind of processes, are well known. So this is nuclear physics, and this we know. We can count neutrinos, we know how much radiogenic heat is there. So in principle, it's very easy. We have to count these neutrinos and to tell, we can tell how much radiogenic heat it is. Of course, it's not so straightforward, because if we measure here some flux, we don't know from where exactly it comes from. The flux here at the Earth, it depends on not only on the abundances, but also on how far is the source of this. So in practice, it's much more complicated and enters the distribution of uranium and thorium and potassium. But this is the real life, as we always know, and I will discuss later on how we can do some approximations and how geological knowledge can help us in this. Nevertheless, the Earth is shining in the flux of about 1 million of geo-neutrinos crossing your finger every second. So a huge number. But let's not forget that neutrinos interact only weakly. So it means that they have very low probability to interact. And I can show you that these numbers are really small with Borexino and also in Kamland and even with large detectors. And also this number, just for a comparison, even if it's big, it's 4 orders of magnitude lower than the flux of solar neutrinos, which are detected in the same detectors, but with a different technique. We'll need a third hand, but okay, so just a reminder about some terminology. So we all know that the Earth was created in the process of the accretion of the small irregular objects, which then as they were bound together, the binding energy was creating the heat. And at some point, the object, when it reached some size, the proto-Earth started to be round, and at some point started to melt. And the first to differentiate was the metallic core, okay, here, and the rest was the melted magma ocean or the primitive mantle. So remember this term, primitive mantle. So it's practically molten rock, so based from silicon, oxygen, and some additional elements, important for us. And what geochemists do today, they are trying to estimate the composition of this primitive mantle, which can be today said that it's like average month composition of the remixed present-day crust and mantle. So the question of what is inside the Earth depends, the answer to this question depends, what are you exactly asking about? Is it the composition, is it the mechanical structure, or the dynamics? So we have heard beautiful presentations, so I don't have to go to many details of this. Important is that we have the inner core, which is metallic, and the very inner part is solid due to the pressure of the overlying layers. The outer core, which has practically the same iron and nickel composition, but with some admixture of the lighter element that we don't know exactly what it is, and we probably will talk about. And it's important in the generation of the geodynamo because it's circulating matter. Then we have a quite mysterious D double prime boundary, core mantle boundary, that we don't understand exactly how does it look like there. And then we have the layer of the silicate rocks. So there we have the mantle. We don't know exactly about its composition. And then we have the upper layer of the crust. We have the 2 types I will tell about. In the mantle is ongoing the convection on the time scale of few centimeters per year. This we know by measuring the speed of the lithospheric tectonic plates by satellites. Lithosphere is composed of the crust, which is chemically different, and on the uppermost mantle, which is similar to the rest of the mantle chemically, but is rigid in deformations, while I see what this is the approximation comparing to the crust, I mean. And it's floating on the more plastic asthenosphere, where the deformations are plastic and not rigid as in the uppermost band. We have two types of the crust, which is important also from the point of view of geo-neutrinos. Along the mid-ocean ridges, in which the mantle plumes are going onto the ocean floor, and the mid-ocean ridge basalts are created and are pushed away in this extension movements. And the oceanic crust can be pulled down under oceanic or continental crust in the deep subduction zones. Then we have the continental crust, which is much thicker, 30 to 70 kilometers, and it's much more complicated in composition. It's the oldest and the most complex object on the Earth, composed of igneous, metamorphic, and sedimentary rocks. And it's very important, and the differences in the uranium and thorium content of these two types of crust is very important, and I comment later on. So how do we learn information about the Earth? We heard already about the seismology. Just to remind, seismology is measuring the propagation of the S and P waves across the Earth. So if there is earthquake, different seismological stations are measuring the arrival of the waves. Seismology from such measurements is constructing such profiles. So the dependence of the speed of the S and P waves and the density across the Earth. Like from this, for example, we know that S waves do not propagate through the outer core. So like that, we know that it's liquid. We can see that, for example, density, there are many discontinuities, which means there are mechanical layers which are different, which not necessarily means that there are layers of the chemical differences, but mechanical, yes. But we don't have any direct information about the chemical composition. Of course, under such pressure and temperatures, not every element can provide such a density. But we don't know directly about the chemistry of the inner Earth. This is the subject of the geochemistry. So, of course, we can take the direct rock samples from the ocean floor morph basalts, or from the beautiful variety and spectrum of the various types of the rocks from the continental crust. But the depth of these direct rock samples is limited. So the deepest borehole, it's only technological channel, but it's only 12 kilometers. And you compare it to 70-kilometer crust under Himalayas, it's really small number. And we have some samples from the upper mantle, which can be brought by volcanism to the surface, or in some tectonic processes, bringing the upper mantle to the surface. But in all these processes, there can be chemical alteration of these xenolites or enclaves. And in addition, they still come from some limited depth. So we don't know really that the deep mantle, which is the majority of the volume of the mantle, what composition it has. For that, the geochemistry is relying on the geochemical modeling, which means that, of course, that we heard, one has to consider the composition of the present day rock. So we observe that the morphs are melted out from the upper mantle, and they have different kind of compositions. As we heard, we have to consider this in the modeling. In addition, there are such beautiful observations that abundance of various elements relative to silicon, as observed in carbonaceous chondrites, so in the one type of meteorites, and in the solar photosphere, are perfectly correlated. So it's reasonable to assume that in the material that from which was the solar system was created was the same. It's the same in meteorites and in the sun. That it was the same also in the proto-Earth. And by putting all this together, you can imagine how many systematic assumptions and so on are there. Geochemists are creating this bulk silicate Earth model, which is the bulk average composition of this primitive ocean, magmatic ocean, which I showed you at the beginning when we discussed how the Earth was created. Which means that if BSE model says there is this amount of kilograms of uranium and thorium, it means that it's the sum of this of the mass of these elements in the lithosphere and in the mantle. And we can say, comparing to the mantle, that we know how much is in the lithosphere, which means crust, one or the other type, plus the rigid upper part of the mantle, continental lithospheric mantle. This blue part of the lithosphere is about 7 to 9 terawatt, from which only 0.2 in the oceanic crust. So majority is coming from the continental crust. Now, then you can do subtraction, the model minus the lithosphere, and you come with what is a huge interval from 1 to 27 terabyte by different BSE models. So there are different categories. We can discuss what exactly, but the take-home message is that this interval is huge. It can be very small or quite a big number. Where this uranium and thorium are expected to be in the Earth. So we have seen a very similar plot during the very nice first talk. Practically, it's showing the condensation temperature of various elements as observed in the Earth, normalized to the abundances of these elements in the chondrites. So if it's 1, it means that the relative abundance is the same as in the chondrites. High temperature means refractory, low temperature, condensation temperature is volatile. Because if you have the low temperature, it means that these elements stayed in the gaseous phase until low temperature, until the Earth cooled, so they had time to escape from the Earth. In simple words. As we can see, uranium and thorium are refractory elements, so it's reasonable to assume that their ratio is such as observed in the chondritic meteorites and in the photosphere. That's why we feel that it's not that we can, because we don't have enough statistics in geo-neutrino measurement to constrain uranium and thorium. Of course, we are trying, and we have heard in the common talk that it's nice to try to confirm this experimentally, that uranium and thorium are actually in such a ratio as the modeling of the Earth is predicting. With potassium, which is more volatile, it's a bit harder to see. Yeah, this is the problem, and we hope in future this community can develop a technique how to measure potassium. Now, uranium and thorium have also the characteristic of being lithophile. It means that they are bound to the silicate parts and not to the metal, which is to the contrary of the siderophile elements. As being green ones, you can see that they are by 2 orders of magnitude depleted in the silicate part of the Earth, because we believe they are bound to the metallic core. Now, lithophile also means that these elements, as uranium and thorium, as you partially melt the rock, I mean, heterogeneous system as the rock does not have a single temperature when it when it melts. So when you heat it, there is the process of partial melting in which the lighter liquid part is melting out from the heavier residual. And uranium and thorium, because of their lithophile property, are always and different radius of their atoms. They are concentrating in this lighter liquid part. So they tend to go higher because they are in the lighter liquid. And it means that they are also concentrated in this most complex continental crust. So this is the estimation of the average concentration of uranium in upper, middle, and lower crust. You see it's depleting. In oceanic crust, which is melted out directly from the mantle, which has much less uranium and thorium, there is an order of magnitude depletion, and in the upper mantle, it's much, much less. And in the core, there is nothing as we expect. So that's why my first slide was wrong. We don't go to the core of Earth studying these geo-neutrinos. Now, this is some estimations. The question is how the uranium and thorium is then distributed in the mantle. The answer is we don't know. Since there is ongoing convection, it's also reasonable that it's homogeneous. In that case, we would obtain the highest geo-neutrino signal. We also heard about some enriched layers or double layer convection. So another assumption is to say, okay, there are two layers. One is more concentrated uranium thorium, and the upper one is more depleted also due to the melting out of the oceanic crust. There could be the lowest signal when all the uranium thorium would be squeezed at the core mantle boundary, and the rest of the mantle would be depleted. So by playing by different distribution of uranium and thorium in the mantle, for a single abundance of uranium and thorium, we can observe different geo-neutrino signal at the experimental site. In addition to this information, we are having inputs about the temperature gradients along the boreholes. There are about 20 to 30,000 around the Earth. And by doing simulations, which also here, we discussed today about the different fluids and hydrothermal fluids along the mid-ocean ridges, when there is a lot of heat ongoing and circulating hot liquids, there we lack the samples. So there is quite some systematic error on the number, like how much from these measured temperature gradients we extract this heat flow. Nevertheless, geophysicists are kind of converging towards this number. I have seen in the slide a little bit different, but we are somewhere there, 47 plus minus few terawatt. So this is the upper limit. So how much heat is coming out from the Earth? There are two main chunks of the contribution to this number. One is the cooling of the Earth from the time, so with the gravitational binding energy of the small object that created the Earth. One part is from core, one part from the mantle. And also here, the intervals are, we don't know how much it is. The rest is the radiogenic heat that we can constrain from with geo-neutrinos. From lithosphere, we relatively well know because we can measure the rocks from the lithosphere, let's say. But from the mantle, it's the same number I've shown before. After you subtract BEC model minus lithosphere, you get the mantle. And by practically measuring geo-neutrinos, you can also constrain the amount of this secular cooling heat, because the total amount is kind of known. So I have already mentioned what are geo-neutrinos, what is the main goal, so the measurement of the radiogenic heat. For that, we need some assumptions about the distribution of radioactive elements in order to predict the geo-neutrino flux, but also from this flux to extract the information about the radiogenic heat. So in this sense, neutrino geoscience is truly an interdisciplinary field. Apart this radiogenic heat, and particularly from the mantle, there are additional questions. By measuring the uranium and thorium bulk ratio, we can get insights about the formation of the Earth and to see if this ratio is the same as we observe in the solar photosphere or in the meteorites. By measuring at different locations, we can also test whether the mantle is homogeneous or not. And we can also constrain the so-called georeactor, which has hypothesis suggestion in the core, as I will show later on. So how much geo-neutrinos we expect? Geo-neutrinos, in order, are expressed, the signal, in the terrestrial neutrino unit, which means one event per 10 to the 32 target protons, because the interaction on which we observe it is the interaction of antineutrino with on proton, so a nucleus of hydrogen. And this corresponds to about 1 kiloton of liquid scintillator per year with 100% detection efficiency. And you can see that from the continent, from the crust, the maximal value is about 50 TNU, which is a small number. Which imagine 1 kiloton, 100% efficiency, 1 kiloton. And when you go to where is Borexino or Kamland, we are about 30. So 30 per year is 1 kiloton detector. When you go to the expectation for the mantle, and this is in the hypothesis that actually below the Africa and the Pacific, the large shear velocity provinces which are observed as the anomalies in the speed of the seismic waves, that they correspond also to the anomalies or inhomogeneities in the distribution of uranium and thorium. In such case, the hottest spot would be about 10 TNU, while on the other side, like 8. So it means that 8 geoneutrino events from the mantle to be observed under 30 or 20 coming from the crust. So it's challenging to constrain the mantle. So now let's have a look for our geology colleagues, what are neutrinos? So neutrinos are elementary particles. We know that they interact only via the weak forces. They have no electric charge. They have no so-called color, so no nuclear forces. And we know that their masses is several orders of magnitude lower than all other fermions, all other elementary particles we know. In order to detect them, they still interact, even with small probability. We need large detectors. We need to go underground to shield the whole setups from the cosmic radiation, which is absorbed in the mountain above, and neutrinos can penetrate. And we need extreme radio purity of the detectors, because it's difficult, in spite of the coincidence stack of the prompt and delay signal, as I will also explain later. It's difficult to distinguish from the radioactive background. Neutrino physics is a very active field, and there are many different questions about the nature of neutrino as the particle. We know there are three types of neutrinos of different masses. We don't know the absolute mass. We don't know the ordering of the so-called mass eigenstates. We don't know if there is an additional sterile neutrino, and so on. It's not so important now. Important is that what we know about neutrino is not what we know. It's sufficient to measure the geo-neutrinos for the purposes we know. It's not limiting our ability to exploit geo-neutrinos as a tool to study the Earth. In this purpose, it's important to mention the effect of neutrino oscillations, which practically means that from the point of creation of neutrino, for example, in the interaction, in the decay of a weak interaction in which the neutrino is created together with charged lepton. So in that moment, if you know that it was born together, for example, with electron, that the neutrino or antineutrino is of electron flavor. During the propagation through the space, there is a non-zero probability that the electron flavor neutrino will be detected as a neutrino of different flavor. This is due to the fact that there are in this matrix which connecting the flavor eigenstate and mass eigenstate, that there are off-diagonal elements. Practically, for the geology community, it doesn't matter. But practically, it means that at the end, you can detect from the original electron antineutrino also other flavors. Now, if your detection interaction is and this probability is dependent on the energy and the baseline of this propagation. Now, as I will show later on, currently we are able to detect only electron flavor. So it means that if the geo-neutrino was born on the other side of the Earth, it has to propagate to my detector, and depending from how much distance it traveled, and exactly also on the energy of the geo-neutrino, I have a different probability to measure it, and only in case, because it could change to different flavor, which is invisible in my detector. I'm able to detect only electron flavor neutrinos. There are different kinds of neutrinos in the world, of different kind of energies coming. I need a little bit of water. So there are different kinds of neutrinos produced by nature or even by humans. They are the same of antineutrinos as geo-neutrinos are coming from the nuclear power plants. We can produce beams of antineutrinos. But today we are speaking about geo-neutrinos, so those coming from the from the decays of long-lived elements in the Earth, which have MeV, so mega electron volts energy, and it is in the same range as reactor antineutrinos. So if you measure geo-neutrinos, the main background is also the antineutrinos from the produced in the nuclear power plants. Until today, only 2 experiments measured geo-neutrinos, as we heard, Kamland in Japan and Borexino in Italy. There are 2 complementary experiment in 2 different geological environments and 2 different parts of the Earth. So it's very interesting to compare the results. At the first, inside they are the same. There is the big ball of liquid scintillator surrounded by photodetectors, so the photosensors which are measuring the scintillation light produced in the detector, surrounded by water pool in which cosmic muons, which are able to penetrate the mountain, produce so-called Cherenkov light, and we can veto such particles which could simulate antineutrino interaction. Originally, Kamland was built to measure reactor antineutrinos. So until the Fukushima disaster in 2011, as we heard, there was quite big background from the nuclear power plants, because it was the main goal of the experiment to measure reactor antineutrinos. In Italy, there are no nuclear power plants. The closest one is in Slovenia, in 400 kilometers from Gran Sasso. So the background was from the beginning of data taking very, very low. Additionally, Borexino was constructed to measure solar neutrinos, which are measured by the elastic scattering of electrons. And this interaction channel requires the liquid scintillator to be much cleaner in radio purity. And Borexino spent many years in the to find and identify how to achieve such radio purity. And it was the unique experiment in the world, which also suppressed the different non-antineutrino backgrounds for the geo-neutrino measurement. So in addition, Kamland is about 3 times bigger than Borexino, and also started data taking 5 years before Borexino. Borexino, on the other hand, is a little bit deeper. So practically there are plus and minus in both experiments, and currently both experiments obtained the latest measurements. As we heard, the currently published results from 2022 by Kamland, and Borexino latest results is from 2020. And with different exposure and different backgrounds and different number of events, we practically reach more or less the same precision. Borexino 17 to 18% and Kamland 15 to 16%. So now I will focus on the Borexino results. This is the picture of Borexino collaboration from our one of the latest big collaboration meeting at Gran Sasso. We are about 100 scientists from Italy, Germany, Russia, France, USA, and Poland. As Nicola was already showing, we are in the underground laboratory close to Rome. There is a highway tunnel, 10 kilometers, and there is a deviation to the underground laboratory. We are shielded by the Gran Sasso mountain. About 280 tons of liquid scintillator is contained in the 100 nanometers balloon, so very thin balloon, which is holding the scintillator, which contains the carbohydrate contains the hydrogen atom. So it's the protons, nuclei of the hydrogen are the target for the geo-neutrinos, surrounded by some buffer as a shield. And these dots are the photosensor which are measuring the scintillation light. Borexino operated from May 2027, and it was discussed. We had to stop in October of the last year. So this is a beautiful photograph taken by a CCD camera mounted inside the detector. We can nicely see the balloon holding the scintillator, the PMTs and some cones which are like focusing the viewpoint to the central part of the detector, some holders on which the balloon for the scintillator is attached. And in case there is a charged particle, it excites the molecule of the liquid scintillator and is producing the isotropic scintillation light. The amount of this light is proportional to the amount of energy which the particle deposited in the scintillator. And by measuring the time pattern of these single photons reaching the photo multipliers, we can reconstruct the barycenter and the position of each event in the liquid scintillator. We need somehow to calibrate the detector. So we inserted the radioactive sources of different particles, gammas, alphas, neutrons, in different positions through the liquid scintillator. And we observed what we observed, how many photons, how well we can reconstruct the position with respect to the known position of the source. We have also inserted external sources, gammas from outside of the detector, and we tested how well we can reconstruct the penetration of the external background to the liquid scintillator. And we, of course, calibrate our photosensors. By doing this, we have tuned and calibrated our Monte Carlo. So it means that we have a system in which we simulate the generation of interaction of the particles, also geo-neutrinos, but also different background components. We simulate the energy deposition in the scintillator, the production of the light, the propagation of the light through the detector, detection on the PMTs, our electronics, and we produce a fake simulated Monte Carlo dataset, which is then treated with the same software that is used for real data. So the same reconstruction. So all the variables which represents the deposited energy, the vertex, pulse shape, and so which means different kind of particles, we run on the Monte Carlo in the same way as on the real data. And here is the comparison of the number of photoelectrons, so kind of energy estimator, for different gamma radioactive sources inserted in the detector as we observed in data and as we simulate. So we have very precise tool how to simulate response of our detector. So electron flavor antineutrinos, so those geo-neutrinos which did not turn to another flavor, interact with proton in our liquid scintillator and produce a positron and neutron. Now the positron, which is an antiparticle to electron, first it deposits its kinetic energy. After that, it annihilates this electron which is around from the liquid scintillator and produce two annihilation gammas. Now, this process of the deposition of the kinetic energy of positron and annihilation is very quick. So we observe it all together as one signal. In this process, the proton is turned to neutron. Neutron is heavier. So there is 1.8 MeV threshold. So it means incoming antineutrino, if it has less energy than this threshold, cannot turn the proton to neutron. At this exactly energy, the poor neutrino turned proton to neutron, but the positron did not get any energy to deposit. So for antineutrinos at this energy, we have exactly 1 MeV coming from the two annihilation gammas of the prompt signal. So What is important to know is the energy of this first signal coming from the positron, which is directly in a practically linear relation with the energy of the antineutrino and the energy of the geo-neutrino. Therefore, we analyze the energy spectra of the first prompt signal. Now, the neutron is wandering around, thermalizing, and at some point, it's captured typically on neutron, on proton. It's born in the excited state, then it excites and emits 2.2 MeV gamma. Now, this gamma can be detected, and it's like a tech, because this capture is ongoing within a certain time, about 200 microseconds, and nearby the capture point. So by searching for time and space coincidence between the prompt and delayed signal, we can pinpoint this interaction. Now, how do we predict how many geo-neutrinos we detect? So we know the energy spectra of antineutrinos, geo-neutrinos from each kind of decay, from uranium, thorium, and potassium. This is the kinematic threshold of this interaction. As we can see, above this, it's only the tail of uranium and thorium that we can measure, while potassium, it's completely out of the reach of the current techniques. To calculate the expected signal in my detector, I also have to know how much uranium and thorium is around. As it was shown before, and as I also discussed, in the continental crust around the detector, there is a lot of uranium and thorium. And from the area of few hundred kilometers is coming about 50% of my signal. So it means I have to know quite precisely the uranium and thorium distribution around the experimental site. Still, there is much more in the crust, but as I go farther, I can do approximations. There are geological models of the like voxels of 1 times 1 degree, I think, databases, which says what is the layer of the lower, middle, and upper crust. And one can use the average composition of the lower, middle, and upper crust. And if I know the average thickness, average composition, I can integrate around. For the mantle, I have to come to the BSC model, subtract what I have in the lithosphere, and play with the distribution as I was showing through the mantle. Then if I know the cross-section, so it's so-called practically probability that the geo-neutrino interact with my hydrogen atom in my detector, I know the oscillation probability. So the probability that my electron flavor geo-neutrino remains such, so I can see there is the interaction. I can calculate the energy shape of my uranium and thorium antineutrinos detected in my detector, starting from 1.8 MeV, and calculate the TNU, the terrestrial neutrino units, the number of interactions that I expect. And in Borexino, we came to about this 28 to 45 MeV, which agrees with the map I was showing, the average signal through the Earth. From this, about 26 is coming from the lithosphere. So there is a huge interval which can be, in principle, allowed from the mantle. Just to say, there was around the Gran Sasso, there was performed a survey of the composition and the structure of the crust around the Gran Sasso, taken many samples. This was done also by the group in Ferrara, by Fabio Mantovani, who could not come. So this is the article from 2011. This work is, however, not performed by the Borexino collaboration. It was in collaboration with geologists and by professionals who understand these things well. We have discussed neutrino oscillations. There is one more detail, as I was saying, that there are these oscillation patterns, which the full cycle of the oscillations for the energies of about 3 MeV as the typical energy of geo-neutrinos or the endpoint, it's about 100 kilometers. If you imagine how big is the Earth, so there are many oscillation cycles which practically means that if you have a continuous source of geo-neutrinos, and they can do many oscillation cycles before they come to your detector, you can consider that there is just an average suppression of the electron flavored flux of geo-neutrinos without the spectral deformation. It's not fully true, because if you have some geo-neutrinos coming from nearby detector, there is some effect that the probability depends on the baseline, which is short and less than the few cycles of the oscillation. But this effect is much smaller than this 15 to 18 precision of the current precision of the experiment. So it does not have to be taken into account so far, the spectral deformation. Of course, for reactor, you cannot do this because you have from one nuclear power plant, which is exactly some distance from far away, and you have to calculate it from all reactors around the world and sum it and get the shape of your expected signal from reactors. I was saying that the charged particles produce the scintillation light. Now, both in positrons, there is annihilation gamma, and the delayed neutron signal from neutron is also gamma. But gamma has no charge. So what happens? Gamma is scattering of electrons. It's so-called Compton Compton scattering. And practically at the end, it's the scattered electron, and actually many of them, which are producing the scintillation light. So there is a cloud of very quickly produced, fast produced electrons, which are producing this the light from the interaction of the gamma and the scintillator. At the end, we measure the two events. We can reconstruct for each energy and vertex, and each of them has a GPS time when the detector trigger. So we can search for the space and times of coincidences, and we have to tune more precisely the cut on of all these events. I don't go through all these details, but just to tell you that for each of the cut on the energy, time, space, distance, veto from the cosmic muons which are still detected, the shape in the position in the fiducial volume of the detector, some pulse shape multiplicity to suppress the background, very detailed work. And at the end, we found 154 candidates, IBD candidates that we had to test, that they all have parameters such as we expect, that they are homogeneously distributed in time through the detector, that the spectrum of prompt and delayed is compatible from what we expect, and so on. We covered the data from beginning of data taking from 2007 to April 2019 with the exposure of 1.3 10 to the 32 protons times years. And like that, we have these 154 IBD coincidences that can be due to geo-neutrinos, reactor antineutrinos, or non-antineutrino backgrounds. Now, what kind of non-antineutrino backgrounds there can be? So there are three main classes. One is the cosmogenic background. So if the cosmic muon still penetrates the mountain, it can produce neutron, which can even from outside come to the detector. A neutron can scatter a proton, for example, and create the prompt signal, and neutron is captured as neutron, so it's the same delayed signal. If the neutron is passing, the muon is passing through the liquid scintillator, it can create lithium and helium isotopes, which decays to electron plus neutron, which is the same IBD-like event, one prompt and then neutron capture. So we have to somehow understand this background. If you have the some radioactive background in your detector, so two completely uncorrelated events can simulate a coincidence. So we call it accidental background. There are also some interactions of the alpha particles. So if there are, for example, polonium-210, which you have in the detector, can interact on this carbon-14, which is an isotope which you have in your organic liquid scintillator, and can produce some IBD-like background events. For all of these events, there was again a lot of detailed work we had studied them, how much cosmogenic, how much alpha n, how much accidental. There are techniques from extra like special analysis of your data or simulations. And after all this detailed work, we find out that we expect about 8 events among the 154 IBD events of background which are not antineutrinos. We also calculated how many reactor antineutrinos we expect. We had to consider the oscillation from all reactors. We got the information from all board reactors. We considered the systematic, the famous bump in the energy spectrum at the 5 MeV. We also studied the signal of coming from atmospheric neutrinos that at these energies, MeV energies, it's poorly known. So we treated it as the systematic error, and the predicted signal, we considered 50% error on this prediction of the overall number of events, which is anywhere a small number of events. And at the end, we did the energy, the fit on the energy spectrum of our prompt candidates, which are bound to the energy of original geo-neutrino. We keep both geo-neutrino and reactor contribution. So this is the blue is geo-neutrino, in which uranium and thorium are fixed to the chondritic ratio. And in yellow or orange are the reactor antineutrinos. We know how much we expect, but we don't put this information in the feed. We keep it free. The 8 non-antineutrino backgrounds events, which I was speaking, the cosmogenic, accidentals, and so on, are these black and green and red, almost invisible. And since we have techniques how to constrain them, the amount of them is constrained in the feed within the precision, how well we know how many they are. At the end, the result of the fit is the number of reactor events, so the area of this orange plot, and number of geo-neutrinos, the area of the blue. These are the vertical lines, the prediction of the number of reactors with the 2 big background shapes. We can see that our fit perfectly agrees with the prediction. So this is something which we really like. It's beautiful. It shows that we are able to measure reactor neutrinos. And the rest are geo-neutrinos. So about 53 geo-neutrinos in 10 years of data with about 17 to 18% precision. Now, this number of geo-neutrinos, knowing the efficiency of which is about 80% of our selection criteria, we can convert and knowing the exposure, we can convert the number of events to the terrestrial neutrino units. So per 110 to the 32 protons and 100% detection efficiency in 1 year, in order to easier compare the signals, for example, with Kamland or other future detectors. And we compare this signal for the signal predicted by different geological models. You can see that from the local crust and the lithosphere, so these 2 colors, it's the same for all BSC models, because this we know. And we say the rest from the BSC model is how much is allowed for the mantle. And you can clearly see that you consider this 1 sigma error, and these error bars, they are compatible with, but we have the preference for the models predicting higher uranium and thorium amount in the mantle. Here is my attempt to do comparison with Kamland. So we have seen these nice results from the latest 2022 paper. This is the spectrum shown to the endpoint of reactor antineutrinos. Here it is shown to the endpoint of the geo-neutrinos, so about here. And the 3 periods, the first phase after the purification of liquid scintillator, and the beautiful data when after the Fukushima disaster, when the blue part is coming from geo-neutrinos. So overall, Kamland has the exposure, which is about 6 times bigger, 5-6 times bigger than Borexino. Overall, we detected about 154 IBD events, from which about 90 is in the geo-neutrino energy window. Kamland in the geo-neutrino energy window detected 1,200, because of the larger amount of background in the previous periods. From this, by doing the fits, I explained how we do fit. We have heard in the previous talk how Kamland is doing the fit. And overall, Borexino detected 53 and geo-neutrinos 183 geo-neutrinos with the precision between 17, 18 and 15 to 16% in Kamland. So we both experiments try to do the fit with uranium and thorium fit free. Now, we have done in Borexino a sensitivity study, like whether we are able to extract uranium and thorium, which means we have done many Monte Carlo simulations of real experiments in which we inserted this kind of thorium and uranium signal ratio. So with some statistical variation, this is the signal. The result was that most of the cases, the thorium is railing to zero or it's flat practically the distribution. So Borexino does not have sensitivity. And even if with some reasonable exposure, that it's very difficult to measure it. So therefore, we don't comment on the thorium and uranium ratio. Nevertheless, we have done fit with the uranium and thorium free, and we measure this number of events. This is to be compared with the plot which we have already seen. I have taken this from the latest Kamland paper, the number of uranium and thorium events. So practically you see 1 sigma, we are both here, 2 sigma in Borexino is touching 0 in both cases, but in Kamland it's nicely here at this part, uranium is much nicer separated from 0. So in order to extract the Mantis signal, it's important to know the amount of the geo-neutrinos coming from the crust. There was done the geological study I mentioned in Borexino around the signal, around the crust, around the experimental site, plus this integration with some approximation of the crust farther away. And we constrained in the fit the signal expected from the lithosphere, and we left free the amount of the signal coming from the mantle, such in a way that the uranium and thorium ratio in the bulk of the Earth is kept the chondritic ratio. Like that, we observed about 24 mantle events, which overall excludes the non-zero mantle signal at 99% confidence level. Now, how this number of mantle events can be transferred to radiogenic heat. It's not an easy process because it depends also on the distribution of uranium and thorium in the Earth, in the mantle. But by doing such different considerations about this distribution, we can have a mantle signal transfer to about 25 plus minus 10, 11 terawatt. To this, one somehow has to consider the potassium signal. So while we know how much there is uranium and thorium and potassium radiogenic heat in the lithosphere, let's say we know, it's much more uncertain how much there is potassium with respect to the uranium and thorium. There are some models, and if we did this, there is about 38 terawatt of the whole radiogenic Earth heat compared to the 47 terawatt, which is the upper limit. If we convert this number of mantle heat to the convective Urey ratio, we obtain the number of 0.78 plus minus 0.34. So again, we are somewhere preferring the BSC models, 5 minutes, okay. But BSC models which are predicting the higher amount of uranium and thorium. I did not succeed to find the updated Kamland plot of this, but this is exactly the same plot, amount of uranium, the signal converted to radiogenic heat for different categories of different BSC models. I think it's amazing that our both measurements agree with the predictions. Now, the statistical error is still big, but there is kind of discrepancy at the level of 2 sigma in a way that Borexino prefers those from the higher end
while Kamland is preferring those from the lower end of the BSE models. But still, 2 sigma in physics does not mean an exclusion. In addition, it assumes that the mantle below the 2 experiments is the same, which might be not true. I have also mentioned that we can constrain the idea that at the core mantle boundary or inside the core, there is fission of uranium ongoing as an additional georeactor. By study this not geo-neutrinos, these fission neutrinos would have similar energy spectrum as reactor antineutrinos. And since those from the nuclear power plants we can predict, we can do an upper limit on the amount of neutrinos from the potential georeactor. And we place the limits according to different positions of this potential georeactor, from 0.5 if it would be near one, or from up to the 6 terawatts if it would be at the farther point from the detector. So this brings me to the summary. Borexino provided a new geo-neutrino measurement with all the data up to April 2019. As we can see the evolution of the different Borexino measurements. We have done all what we did to summarize the number of, to take everything out from our data. And unfortunately, we stopped data taking, so we don't expect additional updates. But we want more, of course. We need more statistics. In future, we need some multi-site experiments or an experiment at geologically particular locations. We heard also from Kamland, they continue to take data, but there are also next generation experiments. SNO Plus, which is a detector in Canada, focused on the double beta decay, but they still is a liquid scintillator detector also, and they still can measure about 30 to 40 geo-neutrinos per year. They are being filled or probably already filled, so I hope in the next years we get some data. There is a Juno experiment, which is in which I'm also now involved since many years actually, and it's the 20 kiloton detector, so 60 times bigger than Borexino and 20 times bigger than Kamland, roughly speaking, and will be completed next year. And in 1 year, it expects about 400 geo-neutrinos, so about double than the current world sample. Because there is an experiment which is focused on measuring reactor neutrinos, the signal is buried under reactors. Nevertheless, with such huge statistics, we expect to achieve the precision of about of Borexino and Kamland in 1 year. And then in several years, we can measure uranium and thorium individually with high statistical significance. Nevertheless, I come back to this slide. My preferred geo-neutrino detector would be something that nobody wants to pay for. So to place the liquid scintillator detector at the ocean floor and to measure directly mantle geo-neutrinos. So let's see what the future will bring. And I finish with the photo of Mount Everest, which demonstrates how much power is inside the Earth. So thank you for your attention. Questions? No? I killed everybody.
Thanks for the talk. So beneath Italy, there is a subduction. Yeah. Let's say Adriatic plate that subducts towards the west. So when you convey the idea that the mantle is somewhat uniform, homogeneous on something, I was thinking, well, but what if this subducted material could somewhat play a role and add some signal? Because you subtract the crust, you think the mantle is homogeneous, but the mantle beneath Italy is not homogeneous. And you take seismic tomography and you see something going on. So did somebody think about it or not?
I don't think that the subduction zone was considered. Yes, sure.
ask two small questions. The first one, in Juno, we don't expect any reactor off time ever, right?
No.
Okay.
Yeah, that was short. No. I mean,
Okay.
some reactors are already running and they will not certainly not stop all of them at one moment for us.
And the second question is not so much on your topic, but you mentioned that there is no S-wave propagation in the outer core.
Mhm.
So how do you get S-waves in the inner core? You can't go through the outer core.
Please. Save me. Save me. It's a phenomenon that is called P to S conversion. So a P wave arrives, and this is compressional wave. And once it is hits the surface where you have a velocity difference, part of a P wave is refracted, some is reflected, but then you also generate an S wave. So it's an S with polarized with some component in vertical. And so you can travel as a P wave in the core, then hit the inner core, and there you can travel as a S wave and so on and so forth. So yes, you can have both. You can recover some signal. Thanks for the question and for the answer.
Perfect answer. Thanks. Other questions? Okay.
You had the sort of three different models of the Earth, the homogeneous and the two different layers. Did you also consider a model that distinguishes the large low velocity provinces from the rest of the mantle? And would it make a difference if you did?
I mean, I have shown the predictions of the predicted signal, but in the conversion and interpretation of the measured signal, it's kind of we don't have sufficiently precise measurements. So we considered in the conversion of the signal to the radiogenic heat all the scenarios that all uranium thorium, which is predicted to be in the mantle, is squeezed at the core mantle boundary, 2 layers on homogeneous. So reshuffling it a little bit within laterally does not make much difference. It's within this error that we considered.
Okay, so other questions? No.
Okay, thank you.
Okay. But I think that also Jinping could contribute in principle because
Yes,
it's very deep,
yeah.
to my opinion, they have a good chance probably.
Yes, but they are on the 70 kilometers back. So the measure
Sorry, but I would like to say that we are very unlucky today because Fabio Mantovani did not come because he had a big problem in his family. And now Bisani had to leave early because he has a much more big problem in his family. So I think that what you can do is to leave to him talk now, then you have the coffee break. And unfortunately, your talk is not included in the concluding remarks, but I'm sorry, this is out our possibilities.
So in the meantime, I would like to thank you for this invitation. So I would like to thank for the invitation and my talk, this concluding remark, in fact, refers mostly to geo-neutrino. So in a sense, it's wrapping back up what it is present, and Joan is future. So in the sense, and in this sense, it could be. So the discussion, I mean, this is just, say, an introduction, and this is the outline of the talk. I would like to draw some very general connections of this science we are discussing, this new science, which is geo-neutrinos, which is very general and very in line with Nicola's remarks, relevance of neutrino studies, in a very general term, again, repeating what was explained very well by previous two speaker, and then a few concluding words. So this is that general. So Greece. So when we think to earth science as a function, this is a very old one. And you may see that Parmenides, according to Diogenes Laertius, was discredited to be having discovered the spherical earth. So, and this is a theorem according to Archimedes. Archimedes postulating that the earth was fluid, was able to prove that the shape was spherical. So this was a theorem, in fact. Eratosthenes measurement, as we know, and the other point that was discussed. But besides this, say, global view, this is not an exclusive passion, because even the ideas concerning micro physics, micro constitution of matter was already discussed there. So since Empedocles, the pluralist, I mean, Democritus for atoms, this is an idea of what is the constitutional, inner constitution of matter. So somehow this arche, this basic matter which constitute things. And as you see again, Archimedes now is credited for hydrostatics, which is mostly relevant for what we are discussing, etc. So what I mean is that microphysics studies and macrophysics study went together since the beginning. And this is pretty amazing, because yesterday on preparing the talk, I realized this beautiful book of Schrödinger about nature and the Greeks. So discussing Thales, that is the first philosopher, the first scientist, maybe, he remarked that the idea of water, we know this water, which we are taught in philosophy lectures, that this might be seen as something anticipating Proust, or maybe just the contrary. Proust was somehow inspired by this kind of search of the basic nature of matter. But even more, look what is there. So he says that this idea of water, not just as water that we know, but as the idea of liquid or even fluid, is anticipating what he says theory of isostasy. This is a paper of 48. So somehow it's before somehow this plate tectonic that we know and we discuss. So what I mean is that there is some deep inner link. We do not want usually to think in this term, because this is so far from us. We would like to be somehow free from past in a sense, but in a sense this shows somehow the way science is transmitted. So somehow in a sense is the love of people for common enterprise and the attempt of surviving together. So now another remark. So this is something much more modern that you certainly know. This is a paper by Norris Russell. This is the Russell Ekström-Russell diagram. This is a paper of 1914, where you see that by studying the composition of the Earth, he was inferring composition of the Sun, and he was concluding that hydrogen is absent in Sun, and helium is absent. So you see there it is written that non-metallic elements are scarce or rare. Okay, and then he was remarking that there is a very similar spectrum for heated material in the composition of the Earth and the one that you observe in the Sun. So he was making a proposal on the Sun composition based on what we know on the Earth. We know this is wrong, of course, but maybe we do not remember that he was the external advisor of Cecilia Payne-Gaposchkin, who is the person who first understood the presence of hydrogen in the Sun. What was the point? You see telescope there, you think it is observation. The point is theory. Again, it's a theory of matter, because hydrogen has a high ionization gap. So somehow the temperature of the Sun is just half electron volt. And instead, in order to ionize hydrogen, you need much higher temperature. So it's not easy to observe hydrogen in the sun. And by correcting with the Bohr model, I mean, we are 25 now, she made first the claim that the sun and stars in the universe contain hydrogen. And this is something that we attribute to Espron-Russell diagram, but in fact, it is Cecilia Pine-Kapowski who made this point, and this point, which was underrated, was considered till long. So what is the point I'm trying to make? I'm just trying to make that we should somehow remember that there is a deep link between what we think and what we somehow understand, what we observe, and the role of theory is not minor since the beginning, and we should be very careful. Now, this other point concerns instead a much more famous story, the one of Kelvin, that we know very well, produced a model which is both incorrect because of geophysical modeling, but also incomplete because radioactive elements were unknown at the time. It was in 1862. But let me point some minor aspect probably. So how is succeed to estimate, how we should succeed to test the age of the Earth through the one of the Sun? The way was this. So he estimated the energy contained in the Sun with this formula. That is basically the Newton constant, the mass of the Sun square over the radius. But as you see, I mean, just mathematically, this formula can produce any result that you want if radius go to 0. So what I'm telling is, Kelvin had in mind that the density of the Sun was almost the same, that there was not the possibility of a very dense Sun in the middle, which would somehow go in the direction of a neutron star or a black hole. Why he thought that density does not change much? Because he had in mind the idea the atoms are indestructible. So somehow, at the time, the idea that atom could be broken did not exist. So somehow, also in this, say, minor aspect, also in this side hypothesis of his thinking, we see the role of microphysics. Now, we know very well that a few years later, radioactivity was discovered by Becquerel, Curie, etc. And then this is, for instance, a famous paper of Rutherford claiming that doomsday is postponed because, I mean, we know we have much more energy and the life can be supported. But and it's very funny that he makes somehow he credits Kelvin for that, but Kelvin was his boss, so this is clearly explainable. But after the access to atom, I mean nucleus and atoms, we had many progresses in science. So somehow in science of the Earth in particular, through say study of crystals, say geochronology, neutron log method by Pontecorvo to search for oil. So neutrons were used immediately for somehow geological purposes, and tomography that was discussed previously. And now we have also neutrinos. Let me continue with neutrino with some general remark, which is much more simple than previous two speaker did. So the core of the theory we are relying on is so-called beta decay. Beta decay is disintegration through emission of electron. Beta ray is the name of electron at Rutherford time. This is the schema of, say, the basic process as understood by Fermi when a neutron transforms into proton, electron, and antineutrino. Now, let me just say in passing, this is pretty disgusting from the philosophical point of view, because you have initially one particle and finally you have other particle in which you transform. This should be said. But once you accept this, and we had to accept it since 30s, the connection with the reaction that we use to detect antineutrino is absolutely direct. You see that there is a straight connection. I mean, the theory relates this process and all kind of process where you switch a particle from one side to the other one transforming them in their own antiparticles. So this is neutron decay. Oh, sorry. This one is the reaction where one proton and antineutrino reacts. So this is the reason why cross-section, why the probability of interaction, as remarked by Livia pretty precisely, is known very precisely, better than 1 per mil. Last calculation was done this year, and the precision of this reaction is, say, infinity for what. So this we know perfectly. Now, through this kind of reaction, neutrinos were discovered by Poltergeist experiment. The evidence of oscillation were obtained by double show, by Kamland in the past, in 2002, 20 years ago. And this was also discussed by previous speaker, but let me make a simple remark, which builds a bit on what Livia told. So you see which is the physics of this process in which neutrinos are transformed. Is that simple. So the neutrino of a certain type, those associated with the electron, Ni is the symbol, are thought as state, as a superposition of state with given mass. And the masses are different. Since masses are different, their frequency of oscillation is different. So if you let them propagate, the final state won't be the same as the initial one. This is the idea of neutrino oscillation. That's simple. And this was tested by Kamland experimentally. It was tested by Borexino low energy neutrino. So this is measured. So we do not need anymore to rely on theory. This theory due to Pontecorvo and Sakata and many other Japanese colleagues, and which was awarded by Nobel Prize given to Super Kamiokande no in 2015. Now, the other point I would like to emphasize that is clearly a big step forward in this science we are discussing is the realization of the ultra pure liquid detector. Why this is so important? Because if we want to study the neutrino, the antineutrino of very low energy, in which we are interested for geo-neutrino, we need to go to low energy. And there are not many chances. For instance, water detectors do not work. They are too dirty and they do not produce enough light. So this is not useful. So we need that. So we do not have anything better. And as I emphasized previously, maybe I can go back here to this point, since the neutron is heavier than proton, there is this threshold. So, I mean, this antineutrino have to kick proton a bit to trigger the reaction. And this is why potassium antineutrino can be seen. So this is the best we can do. The best we can do is to use proton as a target, and unfortunately, we need a bit of help through the antineutrino. And this is why we see only uranium and thorium at the time. So these two photos are taken by John Bacall website, and this is why Gianpaolo and Assudo are a bit younger than they are now. Now, another person I would like to remind in this enterprise is a theorist, was in fact supposed to give this talk, Gianni Fiorentini, together with the other friends, also Fabio, who is not here, and the other one began a systematic investigation of geo-neutrino and all kind of background, reactor, and this was very important for the enterprise, certainly in Italy, because this I can witness personally. And now we have this beginning of geo-neutrino science, these two beautiful results that were discussed by previous two speakers, say Borexino and now also Kamland. And this is, in a sense, my conclusion. Now, let me just remark on a point that Livia flashed a little bit. So let me make a very, very simple point. Suppose we have a certain number of, say, radioactive species, say uranium or thorium, what you want. So some N, a number of, say, radioactive center with a certain lifetime tau. So this is the rate of disintegration. Let me divide by the surface of the Earth. So let me discuss the following point. We know from Newton, no, that if we have a spherical shell, the force is the same. I mean, if you have a mass, a given mass at the center, or you have a shell, the force is identical. Why for geo-neutrino this is not the same? So why this theorem of Newton does not hold? The answer is very simple. So in the case of a gravitational force, we are dealing with the vector. So there is some cancellation. In the case of geo-neutrino, this is a scalar. So this is just sum up. And this is the reason why the result it depends upon the distribution. If, okay, this is an exaggeration. Suppose we have everything at the center, this would be 1 in some unit. If this would be just in the core, this would be increased by 10%. On the other hand, if it was, say, completely uniform, this was larger by 50%. If it was full in the mantle, it is like 60%. If it is just in the upper mantle, is a factor of 2. So this is the kind of, it's just the location of the distribution. I mean, where you put the uranium. The factor is the difference with this case. So somehow, yeah, this would be in a sense say, yeah, the deviation from Newton, say. Okay, this is for fun, no? I mean, just to say that these are the two most interesting cases for what I can understand. And this is the kind of thing we are after. So we want to make measurement such that we can discriminate this from this, for instance. Okay? So this is just, say, half a page of exercise, but just to illustrate it to wide public. Now, in order to put geo-neutrino into context, let me quote this. This is the latest book on, say, neutrinos. It's just now, October 2022. And you see that geo-neutrino are a full chapter of this book. So somehow they are at the same level, they are considered at the same importance as solar neutrino or supernova or atmospheric one. So this is just to stress how important they are considered by physicists today. Now, this is what Joan will discuss, so I will not do it, but let me just say that this is a result I produced 20 years ago. What I mean is that I just mean that this is kind of physics which is standard. So somehow, although for some of us neutrinos or geo-neutrinos are completely new thing, for some people working in the field, this is pretty reasonable assumption. And even the parameter you see, even UE3 was correctly estimated at the time. I will tell you how I did it. So I had the model, of course. And the effect on mantle is the most important one. Deviation from, say, unity can be 70%, 50%. And here you see this is zenith angle cosine. So for when you see deeper and deeper, you see deviation, while the core is a very little angular size and is much more difficult to probe. This is something for future, is not done, and Joan will explain. Last point is that when we consider, so, and as Joan will explain, this is a neutrino with energy which are 1,000 times more energetic than geo-neutrino, 1,000 or 10,000. When we consider neutrino which are million times more energetic than geo-neutrino, we are dealing with what is studied in South Pole at Ice Cube. And they checked that at this energy, the Earth is not anymore transparent. So neutrino starts to be absorbed. In principle, we could learn something about Earth in this manner, but this is handful of events. It doesn't no more. So I don't know whether you will, so you will, so I don't bother you any more. So, okay. Now, this is, of course, I would like to begin summary with a joke, no? So if I say that good science takes geological time, no, this is a joke, of course, in this meeting, you know, but on the other hand, it's true that it takes time to accomplish something sound and reliable. So this is the reason why it is not so common to see a new discipline coming to life, as we are seeing now. And this is why we have a special responsibility toward this kind of science. So somehow now, what we people who understand how precious this could be, I think we should be witness of how important this could be. And I think that recognizing historical roots and links with other lively disciplines is pretty important. And last thing, I would like to make a dedication to Gianni, and I'm using the word of 3 colleagues that for some random reason I just met. So that is Fabio Mantovani, Francesco Lorenzo Villante, and Marcello Lisia. All 3 of them told me the same words. So Gianni is the best physicist I have ever worked with. So this is the person who was supposed to give the talk, and I'm somehow so sorry that is not with us, but let me say a few words on that. I talked many times with Gianni, and Gianni always, he had a very peculiar style in physics. So he produced something simple, clear, and useful. So this is something that, in my view, is almost the definition of science. And with these words, I would like to wish you best success for your enterprise, for science. Thank you.
Thanks a lot, Francesco. And of course, I agree. I had the opportunity to interact many times with Gianni, and I think the same. Yes. Comments or questions? No? No. Okay. Just Gianpaolo.
I want to know if in your wide interest we are working also on the problem of geoscience. Or it's clear that this is connected in some way with geoscience, but we are doing something else on this subject.
You mean for this geo-neutrino, for the future of geo-neutrino, you mean?
No, not only, but also the effect of the geo-neutrino measurement on the Earth, our
Absolutely.
knowledge.
Yeah. So I think we had the very good occasion to talk with 2 colleagues who are renowned experts. I think we should talk with them seriously, and to somehow to plan next move, to know things. I'm very happy that Livia concluded with this statement that we will have Juno soon. It will be some well-defined future for the field, and then Jinping and possibly this Anu. But I think that Gianpaolo wants to ask something else. I'm not sure I understood.
No, but just this is not so important, but also addressed to more to Livia. While I agree that Hano is perhaps the most interesting experiment, but it's not funded for the moment. I hope that in the future will be funded. Also because if I understand, because also in going deeper in ocean, we can have more directly measurement from the mantle. Yes. On the other hand, sorry, I am a little skeptic that in Juno we can do so many measurements, so large measurement of the geo-neutrino, simply because you have the background of something as nine reactors. No, I don't want to discuss now. I know that you no, okay. Now, but you know that we are doing all the possible Monte Carlo, etc., in order to do it. But okay, I am personally too skeptical.
Same feeling before I did the simulation. The point is that the reactor spectrum, we will have a near detector in Taishan, very close to the nuclear power plant, which will be extreme precision of 1% at the resolution at the energy region of interest, will measure very precisely the spectral shape of reactors. If you know this, then above the endpoint of geo-neutrinos, you have practically only reactors. Other non-antineutrino background, we have all the tools, as we also learned in Borexino, you can constrain very precisely from data. So above the endpoint, you have only reactors, and if you measure precisely the shape, you can measure geo-neutrinos. So we can really, we included the expected uncertainty of reactor antineutrino spectral shape, and we can really do what I said. We are convinced. So. But this is accidental background. This you can measure very precisely to 1% by off-time window, as we did. I mean, we have seen also in the first phase of Kamland, the radio purity was also not so high, and they measured. And with the such huge, we will do it, Gianpaolo.
maybe a question of Gianpaolo is ano needed? I mean, I don't know, this is not your question, I understand, but an interesting question is whether this measurement far from continental crust is desirable or needed. So, I mean, a direct search for neutrinos from mantle. This is another question. And I would say this requires a more global assessment. I will not doubt that Juno will do something useful, even improvement, but I don't know whether we can cross completely, or whether this is somehow either desirable or needed. This is my question.
Okay, but I think that by sure it is useful because, as Livia explained, we need a sort of tomography. So even if the detector is placed in different place, they give an important information.
Okay.
So
in order to maybe I should explain better for our colleagues who are not in neutrinos. So neutrinos are useful, this we agree. Neutrinos are expensive, and this we should take into account.
Sure. Yes. Yes, neutrino detectors are quite expensive, of course.
Yeah.
Yes.
Say, Andre added, so is
this clear?
The number is number. Sure, but we should have a clear. Absolutely, I agree.
To say, a few years ago, one person that I don't see this say, but in order to use geo-neutrinos to prevent the earthquakes, I think the only thing is to construct around the world something as, I don't know, 200 Borexenos. And, okay, no, just to say that nobody, some people have not really idea what it means to beat an experiment.
Okay, I understand the point. Yeah. Okay, thank you.
So okay. Thanks. We thanks again, Francesco.
We meet again in half an hour from now for the break with the talk, the very interesting talk of Gioacchino. Thanks. Okay, I think that we started the session, and with the talk of Gioacchino, very interesting talk with the neutrino tomography. Okay, please.
Right. Thanks a lot for the invitation. So I'll try to summarize a little bit some of the things that we've been doing over the past, I think it's almost 40 years now, of studies of how we can use neutrinos to to study the Earth, to do tomography, basically. So yeah, as I said, it's almost 40 years. There's been papers on this since at least the 80s. And there's a long list here, which is probably not even comprehensive of many papers that have been talked about. But I will shamelessly mostly talk about our own paper that we released recently, which I think touches on many of the points that are related to the topic. So just to start, we're going to be talking about neutrinos that are produced in the atmosphere. So these are the source of our neutrinos that we can use. And the point here is not to study the atmosphere, but to study how these neutrinos behave as they go through the Earth, so that we can get information about the center of the Earth. And as you know, because neutrinos don't interact very much, we can then get information about anywhere in the Earth because they really go all the way through. So these neutrinos, they are produced when charged particles, mostly protons, come from space and they hit the top of the atmosphere. And they can have very high energies. They produce a lot of secondary particles after those interactions. In particular, they produce a large number of pions, and pions tend to decay almost always to a muon and a muon neutrino. Those muons then also end up decaying, and they produce a muon neutrino and an electron neutrino. I mean, there are some antineutrinos in there. Overall, if you look at this picture, it shows you more or less the balance that you would expect because of this type of decay that you get. You get roughly equal amounts of pi plus and pi minus. Each pi plus then produces a muon neutrino, each pi minus a anti-muon neutrino. So you get sort of a balance of neutrinos and antineutrinos by this balance of pi plus and pi minus. And then the muons decay into a muon neutrino and electron neutrino. So you get the original muon neutrino from the pion plus a muon neutrino from the muon. And so you get this 2-to-1 ratio of muon and electron neutrinos. It gets a little bit more complicated because of small corrections to it, but you can sort of see that you get this factor of 2 between muon neutrinos here at the top and electron neutrinos at the bottom, with small differences between neutrinos and antineutrinos. So the first thing that you could think of doing with this is just seeing the Earth as if you were taking an X-ray, but using neutrinos. So that would mean that regions that are denser will be more likely to stop those neutrinos, and so you're going to get some sort of contrast. So the main difficulty here, which was already alluded in the previous talk, is that because neutrinos are so difficult to stop, you end up having to go to regions where they're more likely to stop, and those regions are generally at very high energies. The cross-sections, which represent the probability of neutrinos to interact with anything, they grow linearly with the energy of the neutrino. And so only when you reach energies of TeV, so that's 1,000,000 times more than the geo-neutrino energies, is when you start seeing absorption. So this plot sort of shows the expected number of events that you would see in a detector of a gigaton size. So that's also a billion times, or no, 1,000,000 times, let's say, the size of one of these Borexino detectors or Camland. And you would see something like 600 events above a TeV, which is around here, where you can start to see some separation between what would happen if there was no absorption of neutrinos versus if there is absorption. So that means you can actually do this, but your statistical uncertainty will be quite large, and it's even worse than it might seem, because at 1 TeV, the difference is actually quite small. So you actually want to look at more like 10 TeV, and then the number of events really goes down quite quickly. So there are studies that people have done with this. You get some sensitivity, but really to get something useful would be very difficult. It's very hard to build something bigger than a gigaton. Gigaton is at the size that we are right now. Maybe we can get a factor of 10, but it doesn't really improve that much. So for the rest of the talk, I'll mostly talk about neutrino oscillations for that reason, because we can then go actually to a region of about 10 GeV where you get a lot more neutrinos. Unfortunately, usually not a gigaton detector, but still you can do something useful there. So people have already mentioned what neutrino oscillations are. This is another view of what it is. So we talked about how neutrinos are produced in pion decays, and neutrino oscillations, you can think of it as the possibility that in the pion decay, you produce a given lepton, like a muon. When that neutrino that is generated alongside the muon interacts on your detector on the other side, it produces a different lepton. So initially we thought this was impossible. If you produce a mu on one side, you have to produce a mu on the other side. And we found out that it's not impossible. And this is what led to us saying that we discovered neutrino oscillations. So that's basically what we're going to do. The atmosphere produces this side of the picture, and then our detector sees that side, and we sort of try to compare. Of course, we don't know, we don't measure that muon that is produced in the atmosphere directly, at least not for the same interaction, but we do know more or less how many muons are produced in the atmosphere because we measure separately in other experiments what are these fluxes. And we have some idea also from terrestrial experiments on how, when protons hit matter, how many pions do they create and things like that. So the question is then what happens in between from these neutrinos, and what's the probability that that electron is going to show up there as a function of the distance that the neutrino travels. So it turns out that if you measure that neutrino very close to where it was produced, then you expect to see 0. So there's no possibility of that conversion. This is why, in fact, we thought that this was impossible as well, because we measured it immediately and we found no difference. But then if you go to longer distances, and then we represent this in terms of length divided by energy usually, for a 1 GeV neutrino then at 500 kilometers, you expect to see almost full conversion. Technically here, we would talk about neutrinos going from muon to tau neutrinos. There are some details from the fact that here I'm representing things as if there were only 2 neutrinos, so there are actually 3 of them. But the main point is that these oscillations, they happen as a function of this L over E quantity, and then some parameters of the neutrino themselves, which are the differences in masses and the mixing angles. So there's an extra interesting thing that I like to highlight about why neutrino oscillations are also useful. You can actually get full 3D tomography with oscillations, which you cannot do with absorption. So absorption is really like the X-rays, where you get like a 2D picture of whatever came through. And that's sort of represented in this toy model that I put in place. So you can imagine that there is some sort of block of matter here that is about 1,000 kilometers long and has density of 10 grams per cubic centimeter. And then you position it at some distance from you, and there's a source here of mu neutrinos, and you just count how many electron neutrinos are going to get to the other side. Well, I guess the 2 pictures don't represent exactly the same thing. So in one picture here in absorption, you're just looking at how many muons, how many mu neutrinos do you observe, or the difference between what you would have expected. And so all the absorption happens at high energies, and they don't depend on the position that the block is. So the y-axis here is just the position that you put this block along that line. So you get no information about where that block is, just the fact that there is a block there somewhere. But when you do oscillations, you actually see very complicated patterns that, in principle, if you have very good measurement of this pattern as a function of energy, you could tell exactly where that block is along the line. So in principle, this can give you full 3D reconstruction. Now, this ended up to be quite hard because usually the energy measurement is not that good, but it's an interesting thing to think about. So in reality, we're talking about the atmospheric neutrinos, and the pictures look more or less like this. So here now we're showing the energy of the neutrino on the x-axis, and then the y-axis is basically the angle that the neutrino is coming from. So 0 here is if the neutrino is coming horizontally towards you, and then -1 is if it's coming from below, crossing the whole Earth. And so you see these very clear oscillation patterns. So this picture here is the probability that you see a muon in your detector. So if you start with a muon, you see the same muon. So in some cases, that probability is 1, so there's no oscillation happening. And when you see these black bands, the probabilities are close to 0. It means your muon neutrinos have changed to something else. So you're not seeing a muon anymore. On this side is actually looking at the electrons in this case. So you started with muons, and what's the probability that you see an electron? And you see that it's mostly black almost everywhere, except in some regions where you get these large number of electrons that are due to oscillations. And all this interesting structure that happens here and here have to do with the fact that neutrinos oscillate differently if they're going through some matter than they oscillate if they're just in vacuum. And that's what gives us sensitivity to understand the Earth with neutrinos, because they change their oscillations and we can measure that. So to try to understand a little bit better, what is it that we got sensitivity to? What happens is that the matter, it changes the effective mixing between the different mass states that have been talked about before. And this really dramatically can change how neutrinos oscillate. So this picture is showing here, if you consider neutrinos that are going through this path, they're produced in one side, across the Earth and get to your detector. If there was only vacuum in their path, so there was no Earth there, you would see this orange oscillation here, which is more regular, and it's a combination of two frequencies, basically. But when you consider the Earth, you get a very different picture. In some cases, you get suppressions of the oscillation due to the matter. And in some cases, you get these large resonances of large oscillations. And these resonances basically depend on the density of electrons that exists in the path of the neutrino. So the first peak here corresponds to the density of electrons that exists in the core in this path that the neutrino traversed. And the second peak has to do with the mantle part of the path of the neutrino. And they happen at different energies because it's a relationship, it's sort of a ratio of the higher the energy, the lower the density that you're going to get the resonance, that they're anti-correlated in a sense. So what you can do is you can predict more or less where these peaks should be. And then if your density is different than what you expected, those peaks should shift to one side or the other. So all of this that I've been talking about is sort of the underlying theoretical picture that you would see, but of course things are much more complicated in real life. And so I'll go a little bit on what are the things that can make the measurement actually much more difficult. So the first thing to consider is that we don't actually have a source that only produces muon neutrinos, for example, or a single flavor of neutrinos. And so because we cannot control that production at the atmosphere, we have to deal with this and just mix those things together. So you're going to have a flux of electron neutrinos produced, a flux of muon neutrinos produced. And then in your detector, if you look for only muon neutrinos, you're going to see the sum of those with the associated probabilities coming together. Additionally, we also, in most of the detectors that we are considering for the future, you can't really tell neutrinos from antineutrinos. So you also have the flux of antineutrinos to be added into that, which also complicate a little bit the picture. But you can still do things because those fluxes are not the same. You're going to get not full cancellation of everything. And so this picture here shows you what's the expected rate of muon neutrino events plus anti-muon neutrino events. If you consider that the outer core, where the neutrinos are crossing here, is made of pure iron nickel versus some crazy alternative hypothesis that it would be the same as the mantle in its spiralite. Of course, this is not realistic, but it's just to show an exaggerated difference. And so you see the difference between red and black is where your signal would be. And it gives you more or less the same idea that the signal comes in the regions of energy that correspond to this resonance that happens in the core. So it's around 3 GeV that you're going to see some differences and not so much elsewhere. So what we're going to do is then basically do that, but with more realistic scenarios. So we're going to try to put some different materials into the core and see how that changes the probabilities. And in reality, all we care about is this electron density. And so what the different materials will do is that they will have a different proportion of protons and neutrons. And so the proportion of the mass that is of each atom versus the density of electrons will change depending on what the chemical composition is. So for the same density, you can get different values of this Z/A ratio. And that is a proxy for the sensitivity that you have to the electron density. And so here I put some examples of this Z/A ratio for different elements. So you have some distribution here, which doesn't vary by a lot. So the whole range here goes from 0.45 to 0.51. And the only element that is really very different from this is hydrogen, because it only has a proton, so it has one, and then it's completely out of the picture here. And when you consider actual realistic core compositions, they're even closer together. So these are these blue points that you would get corresponding to the different possible models. This is just a sample of the things that geophysicists are thinking about. So then we want to know, can we measure any of these things with current technologies or maybe future technologies? So the first thing you would look at is what's the actual signal that you would expect. So you can represent that as a ratio of the difference of number of events that you would see at each energy and at each direction. So in percentage here. So you'd see a picture that in 2 dimensions looks like that. So every blue region here means you're seeing less events than you would have expected. I think this is it's probably this iron nickel with 1% hydrogen versus pure iron nickel that is producing this picture here. But you have different comparisons there. So the blue regions means you see less events, and the red regions means you see more events. So you could consider looking at specific directions. That would be those dashed lines. And then the pictures would look something like these ones, where you see these up and down patterns. But the reason that you don't want to, you actually want to separate the directions is that if you added these things together, you could see that some of these peaks could cancel out. So you really need to look into these 2 dimensions so that you can disentangle these effects of plus delta n and minus delta n that might happen at different directions. But then life gets more complicated because we are talking about real detectors, and the energies and the directions that we measure in the detector are not going to be exactly the true energy and directions that the neutrinos have. So you have to introduce some sort of resolution there. And then you go from these pictures on the top that I showed before. That picture was for mu neutrinos. There's an equivalent one for electron neutrinos. You go to the bottom ones where you add some resolution effect. And 2 things happen. You get less structure. So all these fast structures sort of disappear in a sense. But you also get smaller amplitude because some of this cancellation starts happening along different energies and along different directions. So while here you see variations of up to 20%, these things go down to about 1% only for realistic detector. And that really is the reason why we need very large detectors, because if you're going to measure a difference of 20%, you can do it with some 50 events or so. But for measuring a difference of 1%, you're now talking about thousands of events. So we considered 3 particular detector examples, and not exactly them, but just an idea of more or less how they work. And they span the range of sizes and resolutions that you might expect from current technologies. So one of them is the DUNE experiment. This is built to measure neutrinos from a beam, but you can also do neutrinos from the atmosphere. It will be the smaller one that we are considering, even though it's one of the largest detectors that were built for this purpose. So proportionally, it would look something like these 4 blocks of 10 kilotons. And it's filled with liquid argon. It's a very expensive technology as well, so it's hard to go much bigger than that. The second one would be Hyper Kamiokande, which is the evolution of Super Kamiokande, making it bigger. It would be at about 400 kilotons. And then we have the Orca detector, which is something that we're building in the Mediterranean Sea right now. So it uses the natural body of water, which helps reduce costs. And so you can go much higher to 7 megatons. So sort of have a 10 times increase from one detector to the other. The Orca detector is basically an array of photomultiplier tubes, so photosensors that you put in 3 dimensions inside this, in the bottom of the sea. It's about 200 by 200 by 200 meters in dimension. And you have about 64,000 TMTs that are going to be put in there. And with those, whenever a neutrino interacts, what will happen is that it will produce a muon, for example, which then produces light through Cherenkov radiation, and that light is seen as a function of time going through the detector. So as a muon goes in here, you can see that all these things go flashing, and we try to reconstruct then what happened from there. So you can get a good idea of what's happened, but it's sort of coarse-grained, especially depending on the distances that you choose for the separation here between these optical sensors. So we tuned those distances to measure what we want, which is these resonances at around 3 to 5 GeV. But you have to balance it between size and resolution. If you make the separation smaller, you can get better resolution, but then your size also gets smaller, or you have to put more photosensors in. There's actually a larger version of Orca that's also being built here in Italy. That's meant to measure very high energy neutrinos above TeV. So you could do the tomography with absorption in that case. But I won't really talk too much about that because I already said that it's not as promising. But this would be a gigaton size versus this 10 megaton or so size. So the next one is Hyper Kamiokande. So you might already be familiar somewhat with Super K. Principle is the same. You have a tank filled with pure water, and you instrument with photosensors the outside of it. So this, because it's not 3D, allows you to get a lot more density of photocathode, and so you can see better the structures of light that are formed. So you form these rings, and this really helps improve energy resolution, direction resolution. But then, because you have to build these things into a tank, it's hard to scale much larger than what this already is, which is 400 kilotons. And so it's already reaching sort of the limit of what we can pay for in a sense. And finally, DUNE is a liquid argon TPC. So the way that this works is that when the neutrino goes in, it produces some particles again, but instead of they're looking for light, although they can see some light, the pattern that really helps is that it ionizes the material, and then the electrons that are produced are then drifted by an electric field and measured through some wire mesh on the side of the detector, and then you can make very detailed pictures of what happened that look something like this in a different detector there, microboon. So with this, you can really get very fine resolution. You can measure a lot of properties of the neutrinos, but unfortunately, scaling all this technology up is kind of hard. So this is sort of the range of things that we can do. For the paper that we wrote, we modeled these things approximately, and we made some assumptions on what is the energy resolution, what is the efficiency that you get as a function of energy, the direction of resolution as well, and the capabilities of them to separate between muon neutrinos and electron neutrinos, because you need that as well to be able to see the oscillations. Just to comment that in reality, you would want to do more than just separate muon and electron neutrinos, and some of the neutrinos can do so. But here we assumed that the only thing that we can do is either we see a muon, which usually looks like a very long particle going through, or you don't see a muon, which means you see some sort of compact object, but that could include both electron neutrinos or tau neutrinos, or events that are produced through what we call neutral currents, where actually the neutrino survives and it just generates a cascade of other particles. And at least for the Orca detector, this all looks pretty much the same. For Dune and Hyper-K, you can actually separate these things somewhat, but we tested it doesn't really make a lot of difference. So from that, you can calculate what's the significance that you would get as a function of energy and direction. So you can sort of make a map of where your significance would be. In the end, what you care about is just the sum of that significance over the whole range, but this gives you an idea of what's happening. So you can see that the scales of the sums are written in the numbers here, and they're about the same for all three detectors, even though they're very different sizes. And they're basically balancing between, again, size and the resolution of the detectors. So the detectors like Orca, which are very large, have very washed out structures, very little structure in the plots, but just the size of them allows you to get large enough overall sensitivity. And as you go to Hyper-K or Dune, you can get more detailed structures, but because of the size, each one of these things, the scale, ends up not helping you as much. So it turns out that all the three experiments end up being similarly sensitive to things. And here we are comparing two extreme cases. So iron nickel versus iron nickel with 1% hydrogen. And you're getting values of delta chi-square, which represent less than 1 sigma by quite a lot. And this is already after 20 years, I believe, in these plots. So it shows that really it's going to be really hard to measure these things. So you can view that in a different way and just compare what is the sensitivity that you get as a function of the variation, this Z/A value for the different detectors. And here the bands represent the difference between whether you can or not separate these other types of events like neutral currents. So you see that there is some improvement you can make, but the bands are not that wide. And these vertical lines represent sort of different hypothesis testing that you could do with realistic models, and the range of Z/A that you would expect to want for having an impact that is meaningful to the geophysics community. And you can see that all the detectors reach a delta chi-square of 1 at values that are far away from this range of delta Z/A. So really, it's not a very optimistic scenario, but it motivates that we should figure out what do we actually need to do to measure this if we want to do this at some point in the future. And so to do that, we try to map out how do these sensitivities change as you change the parameters of your detector. So you make the detector bigger, or you make the energy resolution better, the direction resolution better. So here you have a plot where the size of the detector is given, is related to the amount of exposure that you have. So you multiply the size of the detector with the time running. So we considered a 200 megaton year exposure, which would correspond to something like Orca, so 10 megatons for 20 years. So that's a something that is reasonable that you can build in principle. And then as a function of energy resolution and angular resolution, what is the delta chi-square you're going to get? So if you're in the red region, it means you're not even at 1 sigma level, and so you can't really measure anything. If you're in the yellow region, then you can measure something at between 1 and 2 sigma. If you're in the green region, you're above 2 sigma. So you can see that some of the detectors seem to be in regions that are good, but the problem here is that this is all relating to 200 megaton years. So for a detector like Dune that has only 40 kilotons, then that means 5,000 years would be needed. So it's really not doable in that sense. So to be able to really show the potential of the detectors, you can try to combine energy and angular resolution into one thing. And so we sort of drew a line here through these detectors. And I'm going to say some energy resolution. Now we also associate it with some angular resolution. And then we can compare it to the megaton years on the other side now. So this actually gives you a picture of both resolution and size. And you see that all three detectors are in the red region here. And that's because you can grow in size, but if your resolution gets worse, then your target is moving up and sort of have to get even bigger. So some compromise would be a detector that is somewhere around here. It's about the same size as Orca, but with resolutions that are between Hyper-K and Dune. So that's sort of the goal that you want to have. Whether that's feasible or not, I don't know. It probably would have to be something that is in the sea or in ice, somewhere that you don't have to dig a very large cavern to put things in. But then being able to get the resolutions that you get from Hyper-K without such a controlled environment might be a very difficult thing. But anyway, you can do the same plots with this type of next generation detector, comparing what you would get for different models. And you can see that you can now get curves that go within the range of reasonable models that you're comparing together. And so in principle, you can actually measure this. So if you were to build such a detector, then that could be very interesting, I think, for the geophysics. This is just another way of showing the same thing. We show as a function of time what a detector like this next generation thing would be able to do in terms of separating different models. So this is the precision in the difference in Z over A as a function of time, and then marked in which comparisons of models you'd be able to exclude at 1 sigma, I think, just as landmark. So the most extreme models will be excluded very quickly, and then within 10 years, you'd exclude iron nickel with 1% hydrogen versus something more complicated with light elements, and then you can go to different values. And so you can actually probe quite a few of these models, maybe not all of them. And the final word that I wanted to say is that we're also now starting to look at other possible more complicated things. There are things that we've been told by geophysicists that can be interesting. So you have these LLSVPs that may have different densities, and we don't know exactly what is causing those different velocity profiles. So with neutrinos, you could try to probe whether you can see a difference in densities in a particular region that we know have some anomalies. So we model this in a more or less optimistic way for neutrinos by saying, okay, let's say we had some sort of block of about 1,000 kilometers thickness in some range that is about 45 degrees from the Orca detector. This is more or less where you would expect the African LLSVP to be. And then you look at what would be the sensitivity. So again, for the current detectors, you wouldn't really be able to do very well. You'd see something like, at best case for Orca, something like 25% density resolution there. But with this next gen, you can improve things a bit more and get sub 10% maybe in that type of measurement. It's also interesting to point out that in this case, Orca is a little bit better than everyone else. And that's because we're looking now at mental scale densities, and then the energy where the resonance happens is a little bit higher, and that helps Orca a lot because of the spacing. We can do higher energy better than we can do lower energies. Okay, so just to summarize, I think there's a lot of interesting potential in using neutrinos and in particular oscillations to measure things that can be interesting for geophysics. Unfortunately, with the current detectors, it's going to be difficult to make much of a say that is relevant, but we can sort of show the proof of principle maybe. And if people really find that this is important, maybe we can try to start thinking of a next generation where we could actually make a dent. And I should mention that all of this is done without considering systematics, which can impact things. We have looked a little bit into systematics. It doesn't seem to be really terrible, but a more in-depth study is needed still. So thank you. And these are my collaborators.
Questions?
Thank you. Very interesting. This is what one would call a very visionary talk. I have a couple of much simpler questions. You said that ARCA cannot be used for this kind of analysis, but I missed which is the technical reason why you cannot couple ARCA and ORCA. This is the first question. And the second question, when you said that for this next generation detector, you would need more or less the size of ORCA, more or less, and the resolution of E per K. I am wondering the current resolution of ORCA, how much worse is with respect to E per K? So these two technical issues. Thank you.
Okay, so the problem with ARCA is that in order to make the detector big enough to see astrophysical neutrinos, which is the goal of ARCA, you have to change the spacing to be relatively large. So the spacing is about 36 meters vertically between the optical modules and 90 meters horizontally. And that means that ARCA cannot see neutrinos below about a TeV or so. And at 1 TeV, neutrinos are no longer oscillating, so you cannot do oscillation tomography. You could do the absorption tomography, but then you run into the problem of the number of events is just small. And that's also related to why ARCA is doing that. The flux of cosmic neutrinos starts to get above the atmospheric neutrinos at high energies exactly because the number of atmospheric neutrinos goes down. So this is sort of the reason why ARCA would not be so useful. You could use it, but it's probably not going to give you a lot of information. Then on the question of between ORCA and Hyper-K, the ORCA resolution, let's say energy resolution, is about 25%, while Hyper-K will be more like 10, 12%. This depends on energy, depends on many things. The main reason that ORCA has difficulties is that we cannot reconstruct single particles. We reconstruct the full neutrino event without having much knowledge of the details of what happened. Hyper-K having more density of photons, they can see those rings, and then they can separate potentially 1, 2 pions and things like this, and this really helps reduce the energy. It's unclear for us whether if we use machine learning, if we use some other technique, we can potentially start to do single particle reconstruction in ORCA. It's just very hard to do with the methods, the traditional method that we have right now. So if we can do that, then that could be one way of achieving these resolutions without needing to pay a lot of money to instrument a much denser detector.
But what I didn't understand, in your opinion, it's better to have many small detector distributed or one big detector in one place. It means, for example, between, I don't know, 4 or 5 dune and per country, in your opinion, what is better in order to understand what really you want to understand in the interior of the Earth?
So on one hand, I think for the first order, it doesn't matter. Either option would be equally good. What's important is that you have large enough total volume, whether it's all in one place or separated, it doesn't matter too much. On second order, then it depends on the problem that you're trying to solve. If the problem is something like the core composition, then it really doesn't matter because more or less this is spherically symmetric and the position on the Earth, it doesn't matter. But for the LLSVPs, for example, then it can be useful to have multiple detectors so that you can triangulate things and do a little bit more sensitive. But in the end, as long as you have the megaton years, then it's fine.
Other questions? Also, concerning the previous talks. Livia? No. Okay, so we can close here. I think that we have to thank all the speakers for coming. And I hope that the people here and the people, yes, there is I don't understand. Cosa devo dire? C'è una domanda? Ok. Però?
Just, you know, we had in the past the Neutrino Geoscience conference. This year there was organized a neutrino tomography workshop in Utah. And there we've been discussing about possibility to continue with a merged community because I think it's a pity to split us further to geo-neutrinos and muon tomography and neutrino tomography. So it would be nice maybe to, if people interested, I don't know, if Gianpaolo could provide the mailing list of all people so that if such workshops are organized, and we hope that it will be the case, that we can also inform everybody who was interested to participate here.
Yeah, I should say that we are actually starting already to look into organizing this next year in Paris. We need to make sure that we have the money, the venue and all that, but...
and hopefully 2024 in Mainz, where I will be moving probably, so...
C'è qualche domanda? Niente. Ok. Faccio partire. E chi deve darla? Ah, c'è la persona stessa? Gli comunichiamo che... Ecco. Prego.
Yeah, can you hear me?
Yes, yes.
Yeah, hello, Professor Bellini. This is Sanjeev here. I would just like to add with what Livia just said, that we had this workshop in Utah a few months back, and we had Livia over there, and also Juan Coelho was also there. And I also personally think that we should join the effort, you know, on a global platform saying neutrino tomography. Doesn't matter what neutrino we are using to explore the properties of Earth. And I think we are not in a competition with any seismic or gravitational measurements. We need to show that beyond measuring oscillation parameters, neutrinos can also be sensitive to these issues related to Earth. If we can convince the community about this, then just it's a matter of weight. Like, you know, you make your detector better, bigger, and you will achieve the precision that you want. But I think the question is, what is beyond oscillation with these detectors? And I think there is a lot of scope. because, ultimately the frame is not a measured profile. It's an inferred profile when you combine the data from gravitational measurements and seismic studies. And there are many if then but over there. So we need some direct measurements with weak interactions, which will be complementary. So I just thought that I should share that. And one more comment, Kwan, you presented, one slide, and there was a question about whether we make a bigger detector or a better detector, if I'm correct, right? To achieve neutrino oscillation tomography.
I guess the argument is we need both.
Yeah. So my take is on that there is a trade-off between these two. And your paper that you recently posted in archive, shows some light on that direction, that, what kind of resolution and what kind of detector threshold you need to start probing these issues. But yes, there is a trade-off. Once you satisfy that you have enough event, then you look for better, resolution in zenith and in energy. So yeah, this is a trade-off, and I don't know where is the boundary. It depends on, the question you are asking, right? I exactly don't know where is the boundary. Like, it depends on many things. So the message is like, we should keep improving our detector in size and in properties. This is what I take from your paper.
Yeah, and if I can add to what you said about us providing an independent measurement, the way that I see it is that we have measurements of the S velocity, the P velocity, and with neutrinos you can have a measure of the electron density, which is sort of orthogonal to all those measurements that exist in seismic waves, and you can add a fourth dimension to sort of combine and make a more refined model. So the question is just how much power you can get out of that electron density, and it depends on how well we can measure it, but it can be interesting.
Yeah, like if you measure electron density and if somebody can give you the total density, then you start becoming sensitive to the composition that you showed in your slide. So yeah, definitely you have one more dimension, and also these waves have limitation. They can't pass through, certain areas inside the earth. So this is not the restriction for neutrinos. So I think I completely agree. Like this field is like emerging field, and I think we should join our effort to, combine the effort from geo-neutrinos, from atmospheric neutrinos, and who knows, like even ultra energy cosmic neutrinos, once you will have more events, to say something from absorption. So yeah, I find it very fascinating. And as Livia said, like I requested Kwan that if we can have this workshop next year at APC Paris. So I am waiting to hear from them. And then in 2024, Livia is interested to organize this kind of workshop where we can all, meet and discuss how should we proceed. But one thing, I personally think that if we have more people from geoscience communities, and especially geochemists, then I think the interaction, the exchange of ideas will be very interesting. Having, make them involved in our effort will enrich the field, and we will cross the barrier beyond neutrinos. So maybe that we can consider for future workshop.
Okay, thank you. Other questions? No. So we stop here. Thank you, everybody. I hope that you enjoyed this symposium.